There's only about 20 odd people still in the audience here.
Yeah, they come in. I mean, I think this can wait for if you want 2 minutes more or so.
Oh, well, we'll start at 9. I guess just 9. Spenta is also here now. All right, good morning. Welcome to the third day, and good morning, good afternoon, good evening to participants from various parts of the world. The first speaker today is Ashoke Sen from Harishchandra Research Institute, Allahabad, and he will talk about D-instanton amplitudes, cutting rules, and unitarity and its violation. Over to you, Ashoke.
Okay, so thank you very much. Can you hear me?
Yeah, we can hear you.
Okay. So it's a great honor for me to be speaking at this conference in honor of David Ross. In a sense, he has provided us the motivation for whatever we are doing. Okay, he showed us why gauge theory is relevant for physics, and he also showed us why string theory might be relevant for physics. Okay, and in a sense, that provides a motivation for all our research. So let me begin my talk. So the talk is about cutting rules and unitarity in D-instanton amplitudes, and I'll try to explain the goal of this talk, okay, what we want to achieve. Something is wrong. Okay. So here is a plan. Okay. So I start with a brief introduction to the problem, and then I'll mention what are the problems that we encountered in this analysis. Then I'll describe the remedy. And then I'll discuss some examples in two-dimensional string theory, and I'll stop with some open questions. And please feel free to stop me whenever you have questions. Now, I should just apologize that the first three parts, okay, will be mostly abstract. Okay, you will not see too many equations. Okay. Here, you will be able to see some equations at least. So let me begin with the introduction. So in a quantum field theory, cutting rules relate the imaginary part of the T matrix to T dagger T. Okay, so this is the general form of the unitarity relation, and this is needed to establish that S dagger S is 1, with S being defined as 1 plus IT. Now in a local quantum field theory, this is proved using the largest time equation, and that is a particular property of the position space Green's function. Unfortunately, this cannot be done in string theory or string field theory because the Green's functions that you get from string theory in position space appear to be non-local. Nevertheless, one can prove the cutting rules to all orders in perturbation theory using direct momentum space analysis. Now, as it turns out, in string theory, you can also systematically analyze a class of non-perturbative contributions to the amplitude, but it uses perturbative techniques. And these are the D-instanton contribution to the amplitudes. So D-instantons are D-branes with Dirichlet boundary condition on all non-compact directions, which includes the Euclidean time direction. And the reason that they are relevant in string theory is because they give non-perturbative contribution to string amplitudes that are important in many situations. But nevertheless, these amplitudes can actually be computed using perturbative techniques. And the question that we'll be addressing is, do these amplitudes satisfy cutting rules leading to unitary S matrix? Now, of course, most of us believe that string theory is an internally consistent theory, so it's a unitary theory. Even then, the answer to this question is not totally obvious. And that's because of the following reason. So let's suppose that we have a collision of a pair of gravitons at high energy. So if we have a total center of mass energy that is above 2 over G string, this is in type 2A string theory. At total center of mass energy of above 2 over G string, we can produce a D0 D0 bar pair each of which has mass of 1 over G string. So while testing the cutting rule, if in this sum over intermediate states, we included only the closed string sector, then we will expect that the cutting rules will fail because it will not count the intermediate D0, D0 bar pair which could contribute. So we expect that in closed string scattering at energy above 2 over Gs, we have to include the intermediate D0 branes as in this sum to see unitarity. So if you are asking about cutting rules within the closed string sector, that should fail. Now let's consider collision at energy below 2 over Gs. Naively, one might think that in that case, there is no problem with there should be no problem with the cutting rules. However, there are still possible intermediate D brane configurations that can be produced in this collision. And these are rolling tachyon on D0, D0 bar system. Okay, so I'll just briefly explain what these are. So if we take a coincident D0, D0 bar system, it has a complex tachyon. The maximum of the potential describes the D0, D0 bar system, and the minimum of the potential describes the vacuum without D branes. So here I have just schematically drawn the tachyon potential, but because it's a complex tachyon, you should really think of this as a Mexican hat potential where you revolve it around the vertical axis. But in this system, there are also time-dependent D brane configurations. And that comes as follows, that you can simply place the tachyon anywhere along the slope of the potential. Okay. Take this as the initial condition. And then start rolling. So there are classical solutions in open string theory that has this property. And because you are starting not at the top, okay, where the energy is 2 over Gs, but somewhere down the slope of the potential, it allows, in fact, arbitrary low energy classical configurations in the open string theory. Now you can consider two possibilities. Okay, once you quantize these classical configurations, you can envisage two different possibilities. First is that these are some combination of closed string states. Then, of course, unitarity will be preserved in the closed string sector by itself. But if these represent configurations that are different from closed strings, then you would expect that there will be violation of unitarity within the closed string sector at low energy, okay, because you could produce these configurations at low energy. Now, I should say that this is highly unlikely, because if there really exists such low energy system that is outside the set of states that closed string states span, then it's very hard to imagine how it could not affect perturbative amplitudes. So it will really require exotic matter whose coupling to the normal massless fields, for example, are somewhat unusual because it should not affect the perturbative amplitudes. Nevertheless, this is a possibility you should keep in mind. And clearly, this question one could answer by testing whether the D brane amplitude, whether the closed string amplitude is unitary within the closed string sector. Okay, because if these states really represent new configurations, then you should have violation of unitarity within the closed string sector at low energy. Okay. Now, this is not totally unfounded worry, because a similar situation was analyzed recently in the context of two-dimensional bosonic string theory by Balthazar, Rodriguez and Wynne, okay, well referred to as BRY. Okay. And what they found is that D-instanton amplitudes cause violation of unitarity in the closed string sector in this two-dimensional bosonic string theory. Okay. And this theory, I should just add, maybe I'll say more about it later. Okay. Perturbatively, this is perfectly consistent theory. Okay. Nevertheless, the D-instanton amplitudes do cause violation of unitarity. Okay. Furthermore, in this case, one can also figure out why the unitarity is violated. Okay. And the reason is that there is a dual matrix model description in which everything can be computed explicitly. And when you translate this into the language of string theory, what we find is that the violation of unitarity can actually be traced to possible transition into rolling tachyon configuration, but of a slightly different kind. And this is what I'll try to describe now. So if you consider a D0 brane in bosonic string theory, its tachyon potential takes a slightly different form. It's not symmetric. On one side, so this describes a D0 brane configuration, the maximum. One side has a nice minimum. This describes the vacuum without D brane, without D0 brane. So this height is 1 over G string. But on the other side, the potential is actually unbounded from below. And the non-unitarity of the D-instanton amplitudes that they found, they could identify what it was transiting to. And the answer that they found, again by knowing the results in the matrix model, is that this signal transition from closed string states to the rolling tachyon on the wrong side of the potential. So there are similar rolling tachyon solutions on this side of the potential, and the transition, the non-unitarity basically comes because the closed string states can make transition into these states. Now, unlike in the case of two-dimensional bosonic string theory, in critical superstring theory, we do not have such dual solvable description. And so we have to try to answer this question directly in string theory. And the question that we'll address is, do D-instanton contribution to closed string amplitudes satisfy the cutting rules? As we will see, we will not be able to provide a definitive answer, but we'll be able to identify possible origin of violation of cutting rules and what will be needed to rule out these possibilities. So that finishes the introduction. So now I'll turn to the problems that we face in proving cutting rules for D-instantons. So the usual route for computing perturbative string amplitudes is the worldsheet method. And the worldsheet method essentially expresses the amplitude as an integral over the moduli spaces of Riemann surfaces. But in this approach, what one finds is that the integrand is always real. So the amplitude really has no imaginary part. Given this, one can ask that how can we get the cutting rules? Because cutting rules are supposed to give a formula for the imaginary part of the amplitude. So how do we get cutting rules at all, even in perturbative string amplitude? Now, what one finds in the worldsheet approach is that whenever an amplitude is expected to get an imaginary part, and you can figure this out by assuming that the cutting rules hold, assuming that the theory is unitary, what one finds that the integral over the moduli space diverges. And this means that it has to be defined by analytic continuation. And the analytic continuation of a real function, of course, could give imaginary part. So Witten described a systematic procedure for doing the analytic continuation, and that involves deforming the integration contour into the complexified moduli space. So the moduli space itself, of course, is complex, but this does more than that. So you think of the complex moduli space as, say, 2 real dimensional space, or twice the real dimensional space, and then you complexify again. So this complexified moduli space is in that sense. But it turns out that except in simple cases, it's not easy to actually extract the imaginary part and prove that the amplitude satisfies the cutting rules. So what we can do, however, is to circumvent this by using the language of string field theory. And once we have used the language of string field theory, we can apply the usual techniques of quantum field theory. So let me just say a few words about string field theory. So in string field theory, what happens is the terms in the action of string field theory are constructed from integrals over the moduli spaces of Riemann surfaces of very similar kind that appears in scattering amplitudes, except that the external states are off shell. That's one difference. But more important difference is that the integration avoids the singular regions. So the integration is not over the full moduli space, but only a part of the moduli space, and that part avoids all singular regions. And as a result, the action is finite and real. So there is no divergence in construction of the action. But once you have used the language of quantum field theory, the imaginary parts, of course, come from the usual singularities of the Feynman diagrams. And this can be analyzed in the same way that you do in quantum field theories. But you have to work it directly in momentum space, Right? You cannot use, for example, the largest time equation that is normally used to give a neat proof of the cutting rules in quantum field theories. Now let's turn to D-instanton amplitudes. So open strings describe D-instanton degrees of freedom. So the relevant string field theory that you have to deal with is that of open and closed strings. Okay, you of course have to include the closed strings because these are the external states, asymptotic states. Okay. Open strings are transient states that live on the D-instanton. So the first thing one might ask is that does the field theory of open and closed strings on the D-instanton satisfy the cutting rules? But as we'll try to see now, there are some crucial differences that prevents us from applying the usual derivation of cutting rules to this theory. And I'll illustrate this with the single D-instanton amplitudes, but similar things also happen for multiple D-instantons. So the first problem that we encountered is that the interaction vortices in the open-closed string field theory that we get for the D-instantons, they actually violate energy momentum conservation. And this is related to the breakdown of transition invariance due to the D-instanton. This symmetry is of course restored at the end, but it's restored after integration over the collective modes. But it's not restored at individual interaction vortices. Okay, it restores at the very end as an overall energy momentum conservation. And that means that the usual method for proving the cutting rules does not work. Because the usual method of proving the cutting rules in momentum space uses momentum conservation at each interaction vortex in a crucial way. For example, when you are trying to figure out whether an amplitude is singular or not, okay, you have to do contour deformation in the momentum space. And that contour deformation is subject to momentum conservation. So if the momentum conservation laws don't exist, then the rule of the game changes altogether. So here I have given some examples of Feynman diagrams in this field theory of open and closed strings. So you have both open string propagator and closed string propagator. So my convention will be the thin lines will denote open strings, which carry strictly zero energy and momentum. Thick lines denote closed strings. And in either diagram, individual vortices associated with the Riemann surfaces with boundaries. Okay, so these, for example, the cross diagrams with the vortices with cross describe for individual the interaction terms that come from integration over Riemann surfaces with boundaries. So there is no energy momentum conservation here, okay, or here. So they do not have energy momentum conservation, and for these rules, for this reason, cutting rules are quite different. And in fact, we'll see later that in this case, A has no cut. Whereas if it was a normal Feynman diagram, you would have thought that you can have a cut all through the right through the middle. But we will see that A has no cut. Whereas B, which looks like a tree diagram, and naively you might have thought that it doesn't have a cut, this actually has a cut. So this is just to illustrate that the rules of the game here are quite different. The second complication comes from the fact that for a given D-instanton system, all amplitudes are multiplied by an overall normalization factor. So if you are considering a single D-instanton amplitude, then independently of how many vortices, how many interaction vortices of this kind the corresponding open-closed field theory has, or corresponding Feynman diagram has, the amplitude is multiplied by the overall normalization factor n to the minus c over gs. Just like there is an overall energy momentum conservation from integration over collective modes, but no individual momentum conservation. Similarly, there is no individual factor like this for every vortex, but this is an overall factor. But this clearly causes conflict with the usual cutting rules, because cutting rules relate t minus t dagger to t dagger t. So if you multiply t by some multiplicative constant like n e to the minus c over gs, then of course this will not hold. Right? So here I have illustrated this by this diagram, right? So the cutting rules tells us that the imaginary part of this diagram is given by this cut of this kind. Now this diagram has an overall normalization factor of n e to the minus c over gs, whereas here, once you cut the line, okay, is given by the product of the amplitude on this side and the complex conjugate of the amplitude on that side. This carries n to the minus 1 over gs. This carries n to the minus 1 over gs. So the factor of n to the minus c over gs gets doubled. So clearly these two cannot be equal. The third complication comes from the fact that if you take a generic cut of a Feynman diagram of open closed string field theory, then that will cut both open and closed strings. Okay, so here I have illustrated this. The thick lines again are closed strings. The thin line is open string. So this will cut both open and closed strings. And this will mean that the intermediate state that you are summing over has two closed strings and one open string. But open strings, of course, are not asymptotic states, because they are transient states that live on the D-instanton. So they should not appear in the sum over intermediate states in the cutting rules. So the conclusion is that the usual cutting rules that are neither desirable because of this problem, nor are they provable because of the two earlier problems that I mentioned in the open closed string field theory on D-instantons. So you have to do something different. So here I suggest the remedy, what we have to do differently. And the remedy is reasonably simple. It says that we simply integrate out the open string modes completely and construct what we will call the closed string effective field theory. So in the language of Feynman diagrams, what it does is that it organizes the Feynman diagrams in a somewhat different way. It collapses different interaction vortices and open string propagators into a single composite vortex, which I'll denote by this field circle. And that composite vortex is the composite vortex of the closed string effective field theory. So this, in a sense, is the usual notion that we use in integrating out a set of modes. But there is some difference that I'll mention later. So here I have given an example. So we had seen this diagram in open closed string field theory. And if you want to represent this as a Feynman diagram in the closed string effective field theory, we collapse these two vortices and the open string propagator into a single composite vortex. So you get a diagram like this. On the other hand, this diagram, which started its life as a disconnected diagram, if you want to associate a Feynman diagram in the closed string effective field theory with this, you have to collapse all these three vortices into a single composite vortex, and that's this diagram. And now we see why A doesn't have a cut, whereas B has a cut, right? Because A cut of course cannot pass the vortex, so this is a closed loop, so there is no way you can cut this diagram, whereas this can be cut right through the middle. So the intuition that you get for the cutting rules in the open closed string field theory are different from the actual cutting rules, which you'll be using the closed string effective field theory.
Ashok,
Yes.
could you take a question at this point? Haridas has a question.
Okay, yes.
Just for clarification. Haridas,
Okay.
please unmute yourself and go ahead. He's not responding, but his question is that there are instantons in ordinary quantum field theory also. So
Yes.
why don't you see this there?
Well, the point is for the instantons in ordinary quantum field theory, we do not have a fully systematic procedure, right? Because the modes around the instanton are very difficult to analyze. D-instantons are somewhere in between, right? In the sense that their action is 1 over G string, not 1 over G string squared. And we do have a fully systematic perturbative procedure for carrying out expansion around D-instantons. Okay, that's all we are using here. But of course, this question will also come for instantons in quantum field theory if we have a systematic procedure for analyzing the amplitudes around instantons. Okay, so let me go ahead. So if you have a composite interaction vortex, okay, and that's the closed string composite interaction vortex, okay, this now has the usual momentum conservation laws. Okay, and the reason is simple, because the momentum conservation was violated at each vortex. But as I said, after integration over the collective modes, the overall momentum conservation is preserved. So once you have collapsed all the vortices into one, then of course the momentum conservation is preserved. Okay, this is an ordinary vortex. So here momentum conservation works just as in normal quantum field theory. Okay. This is this composite vortex, but here momentum conservation works because the lack of momentum conservation at these three vortices have all gotten cancelled when you combine them into one composite vortex. So the composite interaction vortex has the usual momentum conservation laws, and it also carries a factor of n to the minus c over gs. Okay, so this now you can think of as a factor associated with the interaction vortex. And with some effort, one can show that the resulting action satisfies the Batalyan-Minkowski-Master equation, just like its parent theory. And I should just add that it follows from, but not the same as, a different notion of integrating out open string modes on conventional D branes. And the difference is that on conventional D branes, suppose you had a D3 brane on which you are trying to do open closed string field theory. There, if you try to integrate out the open string modes, you will not sum over disconnected diagrams. This is somewhat special to D-instantons, that you have to sum over connected and disconnected diagrams to construct an effective field theory. So the proof is slightly different from the conventional proof, but one can show that indeed the action satisfies the VV-master equation. And that in turn means that the action has gauge invariance that is needed for decoupling of the unphysical states. So this can be done systematically also for multiple D-instanton amplitudes. And this gives a systematic procedure for constructing composite vortices coming from multiple D-instanton amplitudes. And they give interaction terms of this order, n to the k to the minus kc over gs. And of course, you can use the standard Feynman rules. That means you can, in a Feynman diagram, you can now use this vortex many times. So those will also give multiple instanton contribution. But what we are talking about here is part of the multiple instanton contribution that is not included by repeating this vortex many times, okay, but which has to be included explicitly in the definition of the action itself. So there are such terms that exist. So the strategy is now to try to prove the cutting rules directly in this closed string effective field theory. And here, because the closed string effective field theory has properties that are similar to normal closed string field theory, the same proof as for perturbative amplitudes in closed string field theory holds, provided the action is real. So this is where all the subtleties arise. And so for the rest of the talk will basically be devoted to answering this question, that is the action real? The action that you get by integrating out the open string modes, is it real? Now, often in quantum field theory, we integrate out the heavy modes to construct effective action for light modes. This effective action is real at low energy, but acquires an imaginary part above the threshold of production of the heavy particles. So even though formally you can integrate out the heavy particles and construct an effective action, it's not real for all energies. Above the threshold, it becomes complex. And this is simply a reminder of the fact that the cutting rules will fail at high energy unless you include the heavy modes in the sum over intermediate states. So if you have constructed an effective field theory, you have integrated out certain modes, then by not including them in the sum over final states, you will violate the cutting rules. Now, this situation is different in the present context because the open string modes are not expected to appear as asymptotic states. They are transient modes of the D-instanton. So what we are asking for is exact reality of the action. Okay? We will not be happy if the action is real below a certain threshold. So then the question is the action real? So to answer this question, we need to understand the structure of the interaction vortices of the closed string effective field theory that we constructed. Now, I told you that earlier that closed string field theory vortices, interaction vortices, are given by expressions similar to string amplitudes, except that the external states are off-shell, and that the integration runs over only part of the moduli space where there are no singularities. That's why the effective field theory action is real. The closed string field theory action is real. Here, one finds that the interaction vortices of this closed string effective field theory are still given by integrals of correlation functions of closed string vortex operators on Riemann surfaces with boundaries with two differences. First, they are multiplied by an overall factor of n to the minus c over gs. This was not something that was there in closed string field theory, normal closed string field theory. Furthermore, as in the usual closed string field theory, the integral runs over part of the moduli space that keeps away from singularities associated with closed string degeneration. So this part is the same as in closed string field theory, but it includes regions associated with open string degeneration, like this, like a pinch disk. Okay, so this is like if you have a start with a single disk, it can pinch in the middle. Okay. So these kinds of singularities are included in the definition of the interaction vortex. And that happens because you have integrated out the open string modes. Okay. So this is something you have to guard against. So with this understanding, we can now identify the sources of the imaginary part of the action. So the first source is that the integrand itself could be complex. Okay. It doesn't happen for closed string effective field theory, but what about here? The integrand could be complex. Sorry, it doesn't happen for closed string field theory, but in the closed string effective field theory, the integrand could be complex. We'll see if that happens. The normalization constant n could be complex, right? Because this multiplies the action. So that's the second source. Okay. And a third source will be the divergences from the region of the moduli space that involve open string degeneration. That may require us to treat the integral in a different way, like via analytic continuation. And this could possibly lead to complex contribution. This is exactly what happens in the closed string scattering amplitudes, right? Not in the construction of the action, but in the scattering amplitudes, the imaginary parts come because you have to do analytic continuation. So here, since you have open string degenerations included in this definition of the interaction vortex, that could lead to complex contribution. So what we are going to do is to explore these possibilities in turn and see if any of those could prevent us from proving cutting rules or proving reality of the action. So first question is, can the integrand be complex? As I said, it doesn't happen in closed string field theory. However, in open closed string field theory, the integrand can be complex if the boundary state that describes the D-instanton is complex. That is, if the D-instanton is a complex solution to the equations of motion. And this is not a totally unfounded worry, because the simplest example, the D-instanton in type 2B string theory, actually is a complex solution because it produces imaginary Ramon-Ramon scalar field. So this is described by a complex boundary state. And this will make the contribution, the D-instanton contribution to the closed string effective action complex. But in all known cases where the boundary state is complex, one finds that there is a complex conjugate boundary state that describes the anti-D-instanton. And so when you sum over the contribution from the D-instantons and the anti-D-instantons, we get real contribution. So because of this, the integrand, I mean, we don't know of a single example where the integrand itself is complex. So for this reason, we will not explore this any further. Okay, we will proceed by assuming that the integrand is real, okay, and see if the imaginary part contribution to the action could arise from the other two sources. So the second question is, can n be complex? So now let me just say what physically n represents. So n essentially represents the ratio of the integration measured in open closed string field theory around D-instanton background and closed string field theory around perturbative background. Now the way string field theory is formulated at present, so we cannot calculate this from first principles. But let me just mention that it includes contribution from the one loop determinant of the open string modes. Because the difference between the open closed string field theory on the D-instanton and the closed string field theory is basically the open strings, right? The extra open strings are the things that makes a difference. And so it has to see, because it's a ratio of the integration measure, okay, effectively it includes contribution from the one loop determinant of the open string modes. Now, as I said, unfortunately, it cannot be computed with our current understanding of string field theory. But still, we can say something about it. Okay, and that's what we are going to do now. So for this, let me remind you that D-instantons are classical solutions on the Euclidean theory. So they represent local extrema of the action in the Euclidean string theory. And the open string modes represent fluctuations around this extrema. So if there are only massive and massless open string modes, then we can say that the Euclidean action has a local minimum at the D-instanton. On the other hand, if there are tachyonic open string modes, then the D-instanton is a saddle point of the Euclidean action. And that means that when you draw the steepest descent contour, it has to run along the imaginary axis of the tachyonic modes. So this suggests that we get a factor of I for each tachyonic mode. So whether, even though we cannot calculate n, we can conclude that for every tachyonic mode, n should get a factor of I. And indeed, all known cases where n can be found using duality, either in type 2B theory or in two-dimensional bosonic string theory, it confirms this, that if there are tachyons, then every tachyon contributes I. So we already see that this poses a possible threat to type 2A string theory, where it has a non-BPS D-instanton with a single tachyonic mode. And this would suggest that the associated n will be imaginary, unless of course it is 0. So later we'll discuss the possibility of when n could be 0. Now let me come to the third possibility. That's the imaginary part from the open string degeneration. Now, massive open string modes at the degeneration give finite real contribution, so they are not to worry about. Okay, you can just include that contribution as it is. Tachyons do give divergent contribution from degenerate boundaries, but string field theory replaces it by finite real contribution. So this is something I'll not talk about here. I have discussed this in other talks. What string field theory? So tachyons give divergences of this kind with positive alpha. And string field theory tells us that when you have encountered divergences of this kind at q equal to 0, you replace it by -1 over alpha. So you are replacing a formally real contribution by actually a finite and real contribution. So this also doesn't give any imaginary part. Massless open string modes need special treatment, but this has been reasonably well understood by now, and they also do not seem to generate any imaginary part. So the modes that are problematic are the modes that turn from massive to tachyonic as the D-instantons move, and these require special care. Okay, and I'll try to explain how this happens. So let's suppose that you have a system of two D-instantons. We label them by 1 and 2. And suppose that when they coincide, open strings traced from 1 to 2 and also from 2 to 1 have tachyonic modes of mass square given by -m square. This happens, for example, for the D0 plane in two-dimensional bosonic string theory. And this will also happen for the D0 D0 bar system in type, in the instanton anti-instanton system in type 2B string theory. I shouldn't have said D0 plane, I should have said D-instantons in bosonic string theory. That when they coincide, there is a tachyonic mode. Okay. So now let's consider the case when they are separated by distance x. In this case, the mass square of the tachyon or would-be tachyon is given by x over 2 pi square minus m square. This 1 over 2 pi is a reflection of the fact that the string tension is 1 over 2 pi. X is the separation. So this is the mass square of the tachyons, okay, which stretch between the two D-instantons. So now, because the one loop determinant of a field of mass m gives you 1 over m, okay, you have one loop determinant of two tachyonic modes because there's a complex tachyon, okay, or 1 to 2 and 2 to 1. That will give a factor of x over 2 pi whole square minus m square inverse. Okay. But eventually, of course, you need to integrate over the D-instanton locations over x. Okay. So we see that there is a singularity at x equal to 2 pi m, and we need a prescription for dealing with the singularity at x equal to 2 pi m. And this requires some understanding. So this problem was encountered in this analysis in two-dimensional string theory by BRY, and they suggested a specific procedure for dealing with the divergence. And that procedure was to rotate the Euclidean time integration contour to the Lorentzian time integration contour and define the integral that way. So in that case, you basically replace x over 2 pi square by minus x over 2 pi square. So there is no singularity. But one can show that in the Euclidean path integral, this amounts to defining the integral by a specific I epsilon prescription. Okay, and that's the prescription. Okay, so the Lorentzian integration contour that they use is equivalent to introducing this I epsilon prescription in the Euclidean variable. Okay. Now, notice that in the Lorentzian prescription, it will look real because it's minus x over 2 pi square minus m square. Okay. But what one can show, okay, by keeping track of all the factors of I, is that this I epsilon actually makes the low string effective action complex. So here I have given the procedure for general case where there are multiple instantons and higher order terms. And their Lorentzian prescription will amount to adding an I epsilon here. But as I said, if we follow this prescription, this translates to having a complex contribution to the closed string effective action. And this will clearly lead to violation of cutting rules. So here, I suggest an alternative prescription for dealing with real effective action to lead to real effective action. And that's to average between the Lorentzian contour, which is this one, and this I can call the anti-Lorentzian contour, where we replace all the I epsilons by minus I epsilon. One can show that this prescription leads to real effective action. And this will restore unitarity, provided, of course, n is real. Okay, that's a separate problem. So in principle, the correct contour prescription and whether n vanishes or not should be determined by the Picard-Lefsetz theory applied to string field theory. Maybe I'll say a few words about Picard-Lefsetz theory, but I'll not say too much about it. Okay, before I go on to two-dimensional string theory. So let me just describe briefly how one could possibly apply Picard-Lefsetz theory here. So you note that a system of D-instantons represent a saddle point or a continuous family of saddle points of the Euclidean action. And the contribution from each saddle point is evaluated by carrying out the path integral along the Lefsetz symbol, which is basically a generalization of the steepest descent contour in multidimensional complex space of string fields. And the relevant string fields here are the open string fields, okay, the open strings on the D-instanton, because we are really constructing a closed string effective action, so the external closed strings are kept fixed, and we just integrate over the open string modes. So the second part of the Picard-Lefsetz theory requires us to express the original integration cycle over the string fields as weighted union of these Lefsetz symbols. And of course, there are different Lefsetz symbols associated with different saddle points. And the ambiguities that we encountered, that we mentioned, the ambiguity in n, okay, is n real or complex or zero. And the choice of integration contour, okay, whether to use Lorentzian prescription or unitary prescription, they can be all traced to these weights, okay, the choice of these weights. So with a better understanding of the configuration of open string field theory on D-instantons, we should be able to determine these weights and resolve all the ambiguities. Okay, so it's not that the string theory is intrinsically ambiguous, but you need to have a better understanding of the open string field theory on D-instantons. So once you understand that, we can ask these two questions. Does n vanish for non-BPS D-instanton and type 2 string theory, thereby restoring unitarity within the closed string sector? The second question is for type 2b string theory, are you led to unitary prescription for the integration contour for instanton anti-instanton system in type 2b string theory? Because there again we have the same problem, right? Because you have a tachyon on the open string stretching between the instanton and anti-instanton, and that goes from massive to massless to tachyonic as the instantons and anti-instantons come together. Okay, so with this, in the last a few minutes, let me turn to examples in two-dimensional string theory. And here you will see some explicit illustration of the various abstract reasonings that I gave. So let me remind you that two-dimensional string theory has world-sheet matter theory that is made of a Liouville theory with central charge 25 and a free scalar describing the time coordinate. And the BC ghost system is usual. So physically, this describes the string theory in 1 + 1 dimensions. Liouville field describes the space direction. And the scalar field, of course, describes time coordinate. So in this theory, the physical closed string spectrum has just one massless scalar. And this is called the tachyon, even though it's a massless scalar. Okay, this name basically is inherited from critical string theory. But in two-dimensional string theory, there's one massless scalar, and the perturbation theory seems to be completely well defined. Now, in this case, there is a dual matrix model description, and this can be used to compute the non-perturbative effects in this theory. So the matrix model description can be translated to non-relativistic fermions moving in an inverted harmonic oscillator potential. Of course, the single particle energy levels are unbounded from below because it's inverted harmonic oscillator potential. But there is a sense in which this describes a consistent description of two-dimensional string theory. And this the description that I'm going to use was suggested by these authors, that is more recent. And what they said is that you fill the Fermi level, you fill the one side of the potential up to the Fermi level, and leave the other side empty. Okay, now this of course was understood even in the old days of matrix model. But what they did was to make it more specific. What they said by filling up to the Fermi level is that we first construct the exact energy eigenstates. Okay, so there is a set of energy eigenstates which correspond to incident wave from the right and reflected wave to the right and transmitted wave to the left. That's one set of energy eigenstates. Those are the states that you fill up to the Fermi level. There's an orthogonal set of energy eigenstates which correspond to particles coming in from the left and getting reflected and partly transmitted. So those energy eigenstates will leave empty. So this gives a completely well-defined description of what one means by the vacuum, or the what one means by the vacuum of this theory. Of course, you can construct lower energy states. So in that case, sense, the vacuum is not the lowest energy state, but this identifies a particular energy state that we call the vacuum. So they computed the D-instanton corrections to the amplitudes from string theory side and found unitarity violation. And that, as I've already said, is in agreement to the matrix model result. Matrix model result also shows unitarity violation. And the reason for this unitarity violation, as I've already described, is a transition into rolling tachyon states on the other side of the potential. So the low-lying closed string states around the minimum of the potential can simply tunnel to states on this side of the potential. So now one can ask that does this agree with the general discussion on unitarity of D-instanton amplitudes that we have had? So here what I'll do is that instead of following the historical route, we'll first describe some results in string theory side without referring to the matrix model. And at the end, we'll try to compare this with the matrix model results. Okay, what kind of string theory results we can get based on the discussion we had already in the general context. So we'll focus on closed string two-point function with the external energies omega1, omega2 and external Liouville momentum P1, P2. So we'll take omega1 negative, and call this minus omega1 tilde. This will represent incoming state. Omega2 positive, this will represent outgoing states. And the on-cell condition corresponds to Pi being equal to mod omega by I by 2. So Liouville momentum is always positive because on one side there's a hard one. So by convention, Liouville momentum is taken to be always positive. So we'll begin with the single instanton contribution. So the leading contribution to the single instanton contribution comes from the product of two disk one-point functions. Here I have written this here. So this is the description in the open closed string field theory. And this translates to this particular composite Feynman diagram in the closed string effective field theory, because you are supposed to join these two crosses into a single vortex. And this result was computed by BRY, and this was given by this. Okay, this can be computed from the Liouville theory. And generalization of this to n-point function is straightforward, because the leading or contribution to n-point function is just n of these. Okay, n of these lines. And then when you construct a composite vortex, there will be a single composite vortex from which n lines are coming out. Okay. And this we can translate to the n-point interaction term in the closed string effective action. Okay. And here I have described that here. Okay. N is an as yet unknown constant. Okay. These are integrals. I think everything else has been defined. Oh, B. So B is a constant, a positive constant. Okay. This is a parameter of string field theory. The final results are supposed to be independent of B. But when you construct a particular version of closed string field theory, okay, it comes with some additional parameters, and B is one of those. Okay. So change of B corresponds to field redefinition from the string field theory perspective. Okay. And now we see that for real n, okay, this action is real. Okay. So you should get unitary amplitudes if you choose n to be real. Okay, from the general arguments that we get. Because in this, we can prove the cutting rules. So let's check this, okay, that we are on the right track. So next order is given by the product of an annulus and a disk amplitude. This amplitude is formally real, but one finds that it has a divergent term, okay, which comes from open string degeneration. Sorry, which comes from closed string degeneration, not open string degeneration. Okay, this is amplitude, okay, which is given here. Okay, so this is some constant that comes from Liouville theory, right? 3-point function in Liouville theory. I think everything else has been defined. T1 and T2 are integration variables. Okay. And the point here is that if you just naively look at this, you would conclude that this is real. The integrand is perfectly real. You are integrating over real variables. Okay. Except that the integration over T1 and T2 diverges for T1, T2 going to infinity. Okay. It diverges when omega 1 tilde is larger than 2p1 plus p2. Okay, here. And as a result, we cannot make sense of this integral. Okay. And the way we treat this integral is to use string field theory to make sense of this divergent integral.
5 minutes, Ashok.
Okay, thank you. Okay, so here was the expression. Now, what one finds is that one can identify this to a contribution from this particular Feynman diagram in string field theory. Okay. And this in turn in string field theory is given by an integral of this kind. Okay, this looks like normal Feynman diagram because you have an integration over the energy, integration over the internal momenta. Okay. So this looks like normal Feynman diagram with I epsilon prescription. Okay. Now, what is the connection between this and this? Okay. If we do a Schwinger parameter representation of these propagators, okay, and formally carry out the integration over the Schwinger parameters, integration over the omega, okay, once you have done the Schwinger parameterization, you get to this. Okay. But that manipulation is formal because this integral is actually divergent. Okay. This, on the other hand, is a perfectly finite integral. Okay. String field theory also tells you how to do the integral, which contour to use to do the integral, and it's this contour over here. Okay. So you can calculate this now. This is a finite integral. Okay. And one can calculate in particular twice the imaginary part of this. Okay. Assuming n is real. Okay. This is the answer. And this indeed one can show matches the contribution from the cut diagram, which is given here. Okay. So as expected, okay, as long as you choose n to be real, there is no violation of unitarity. Okay, the unitarity is perfectly fine at the level of 1-instanton amplitudes. So leading 2-instanton contribution to the tachyon 2-point function, I'll just give the result. So if you use a lot, so for 2-instanton contribution, you have to distinguish between Lorentzian and unitary prescription. Even if you choose n to be real, right? The Lorentzian prescription, if you remember, was given by BRY by rotating the contour in the Lorentzian space. Unitary prescription, in some sense, is the average between I epsilon and minus I epsilon prescription in the Euclidean contour integral itself. Okay. So both give imaginary contribution. Okay. But the question is that which one agrees with the cut diagram? Okay. Which one, if any, agrees with the cut diagram? So in this case, the relevant cut diagram is this one. Okay. Here, in fact, you have to sum over multiple closed string insertions. It's an infinite sum, okay. But the sum can be performed. Okay. And one finds that the final result after performing the sum over all the cuts, all the cuts of this diagram, okay, agrees with the unitary prescription. It gives us precisely this result, okay. But it does not agree with the Lorentzian prescription. These are, of course, different expressions. Okay. So again, we see that if we choose n to be real and if we choose unitary prescription, okay, then we restore unitarity. Okay. So this is the conclusion. By taking n to be real and using unitary prescription for multi-instanton amplitudes, we can actually get a unitary bosonic string theory in 2 dimensions. So this, of course, agrees with our general arguments. Now the question is, how did BRY get unitarity violation in their analysis? So for this, we have to go back to that analysis and we can ask, how did they determine the normalization constant? So as I said, from string theory side, you cannot determine the normalization constant from first principle. So they actually determined this by comparing the string theory results with the matrix model results. And they didn't write it this way because they are using a different convention for the normalization where they got a real result. But when you translate their result to the convention that I have been using, okay, one finds that their choice corresponds to choosing n equal to I over 8 pi square. Okay. And this I, in fact, is the sole source of unitarity violation in the 1-instanton sector. Because as we said, as we saw, okay, if we take n to be real, then there is no unitarity violation in the 1-instanton sector. When you go to multi-instanton sector, in 2-dimensional string theory, they have 2 different sources of unitarity violation. One is that they have chosen the n to be imaginary. Okay. And then second source is that they have used Lorentzian prescription for carrying out the contour integral over the D-instanton positions. Okay, so I think I'll just end with some open questions. So there are 2 open questions that I would like to address. First is, we have seen that by choosing real n and unitary prescription, we can get unitary amplitudes in 2-dimensional string theory. So this begs the question, is there a dual matrix model? It's certainly not what they had. Let me go back. See, the matrix model that they described had a potential of this kind. But you can easily convince yourself that the perturbative amplitudes are unmodified if we just have some kind of wall over here on this side. Okay, because whatever you do on this side are not failed by perturbative amplitudes. Okay. The question is it possible to modify this potential or do something to this potential, okay, on the left-hand side, okay, so that we restore unitarity, so that we get a unitary matrix model. And that agrees with the unitary 2-dimensional string theory that we constructed. So that's an open question which may or may not have an answer. The second question, which is of interest, is can we use Picard-Lefsetz theory to resolve all the ambiguities and disprove unitarity of, prove or disprove unitarity of D-instanton amplitudes in the closed string sector itself of critical superstring theories. Now, this may look like a tall order because string field theory itself people are scared of. Okay. And if you're using Picard-Lefsetz theory to string field theory, so that looks even more scary. Okay. But I should just say that it may not really be out of reach, because what we are dealing with here is not the full string field theory, right? Because the modes of the D-instantons are given by open string field theory. These are the ones that are integrating out. Okay. An open string field theory on D-instantons actually has countably infinite number of modes. Okay. But it's not a continuous set like quantum field theories or even quantum mechanics. It has countably infinite number of modes. Furthermore, most of the massive modes can actually be integrated out. They do not give an imaginary part. They are not responsible for anything interesting. So the real players in this game are only a finite number of massless and tachyonic modes. And those, I feel, one should be able to deal with by the standard Picard-Lefsetz theory, which deals with multidimensional integrals of multidimensional but finite dimensional integrals. So these are the 2 questions which may be answerable in the future, and I think I'll stop with this. Thank you.
So let us thank Ashok, unmute ourselves and thank Ashok. So there is about 10 minutes for questions before the next talk begins. Already TRG asked a question here. So TRG, please unmute yourself and ask the question.
Just to know whether the apparent violation of unitarity will appear as anomaly in the effective field theory?
No, I would not say it's an anomaly, right? Because gauge invariance one can show is not broken. What it will appear as is an imaginary term in like effective field theory. So you can have imaginary terms which are gauge invariant, right?
Okay.
Because one can give a formal proof of gauge invariance of the effective field theory. Okay, by standard Bataillon-Minkowski formalism.
Okay. Other questions?
Yeah, I have one question.
Yeah, Ritabh, please go ahead.
So you're saying that by choosing real n and using the unitary prescription, we could possibly prove the cutting rules or the unitarity of the string theory in 2 dimensions. But was it after you integrate out the open string modes and got the effective closed string field theory? That's
Yes,
what I saw.
so this refers to the effective closed string field theory.
But is it sufficient to prove a unitarity for a effective field theory and say that the full theory would be unitarity?
Yeah, because see, the open strings don't appear as asymptotic states, right?
Okay.
So if you can prove unitarity of this effective field theory, that proves the unitarity of the amplitudes, because we don't, we are not including open strings in the final state anyway.
Oh, okay, I see.
Right? If you are integrating out some massive modes, then of course neither do we expect unitarity nor we should be able to prove it, because above the threshold of production of those massive modes, right, you will have unitarity violation because you are ignoring those massive modes in the sum over states.
Okay.
But this is different in this theory because open strings are not asymptotic states.
Okay.
Yeah, Ashok, can I just add to that question? Why should one not include asymptotic open string states in a complete open closed string theory?
Yeah, because the D-instantons are transient objects, right? They are solutions of the Euclidean time coordinate, but the solution actually goes to zero, goes to the perturbative vacuum at -infinity and +infinity.
Yeah, but we are considering a complete open closed string field theory, right? In that, open string state should not be asymptotic state. Is it a complete theory then?
Well, see, if somebody had given you the open closed string field theory and didn't tell you that these are coming from D-instantons, then you might be led to believe that these are asymptotic states, okay? Even though, okay, the fact that you have no energy conservation, okay, already tells you that something is wrong. But for D-instances, we of course certainly know that there is no energy conservation at the vertices, and you also know the reason, okay? And that happens because the D-instantons are transient modes. Okay? It's like if you have QCD instantons. Okay? Instantons have their collective modes, right? There are fluctuations around the instantons. But when you talk about the asymptotic states, right, those are not, you don't include, for example, the translation mode of the instanton as an asymptotic state in the theory. Right? Because those are transient objects.
Okay,
so asymptotic states are fixed once and for all in the closed string field theory. Or if there are other D-branes, right? For example, there is a D3 brane, space filling D3 brane. Then, of course, that open string modes on the D3 branes will also be asymptotic modes. It's because we are considering Euclidean D-instantons, which are localized in time. They don't exist at t equal to -infinity and t equal to +infinity. So where are open strings supported, right?
So when you're saying that open strings are not don't create the asymptotic states, you mean that when we do the means for the internal states, when we do the sum over states, we don't have to include those modes.
Exactly, that's right.
Raghu, please ask your question.
Yeah, hi Ashok. Thanks for the nice talk. I just have a question. I wanted to see whether I understood. So, Is it true that there are two theories here? Are you saying that the BRY prescription leads to one definition of string theory non-perturbatively, and this other one that you are describing is a different definition, and they're dual to two different matrix models? Is that what is happening?
Okay, so I don't know whether what I'm describing is really a fully consistent theory, right? All I have said is that if we choose the normalization constant n to be real, then at least the perturbation theory around the D-instanton seem to give an unitary amplitude. Whether there is actually a dual matrix model, of course, we don't know, right?
So this n being real is an assumption in what you're saying?
Yeah, because the n is not computable, right? As I said, the current understanding of string theory, n is not computable. Right?
I see.
So we put the n in, right? And then we ask, right, that is it possible, for example, to modify the matrix model? Okay, let me put the question from the opposite perspective. Then let's imagine that the potential here actually turned up, okay, far away. It is not going to affect the perturbative part of the amplitude. Now we also expect that any wave that falls in from the right will get reflected eventually, right?
Right.
So there should be no unitarity violation in this. Now that theory, it could be that it's not described by string theory at all. But it's also possible that for some particular choice of the potential on this side, it is actually described by the closed bosonic string theory with real n.
I see. So you're not saying that the n being imaginary that BRY described it's correct, but they're just using this unbounded potential to compute that n being I over 8 pi squared.
Yeah. Okay. So for that particular dual, that they have taken a particular matrix model, right? And their dual is a closed string theory, right, which has imaginary n.
Okay.
So that is not wrong, certainly. I mean that is perfectly sensible. The question is whether there is another matrix model which gives real n. Well, at least from the string theory side, it seems that we can describe unitary amplitude by choosing real n and Lorentzian integration contour. Sorry, not Lorentzian integration contour, by unitary prescription for the integration contour.
Okay, thanks.
Okay, thank you.
Rajesh? Yeah, Rajesh, go ahead.
Hello. Hi. Just sort of following up on that. Supposing you were by hand to just remove the I from their normalization, the I over 8 pi square, can one trace it back in the matrix model to what happens if one were to have to just remove that I? Is that something easy to trace, or maybe it's this thing? And the second sort of this thing, which is more like almost this thing crazy remark, is that maybe could it be that this the continuation of the potential on the left hand side is exactly like the bosonic string bosonic potential, and with a height of 2 over G string? I mean, because in some sense, the eigenvalues that you have in this matrix model potential are like the D-instantons. And maybe this is this potential is really like the bosonic potential. I don't know. Just maybe.
So you are saying that it will turn up like this.
Yeah, and it will be with the height 2 over G, whatever the bosonic.
Yeah, it could be. I mean, I think that these two questions are related, I think. So, I mean, you are asking that if we had taken n to be real, is it possible to figure out what's happening on this side, right?
Yeah.
I feel that it probably is possible, because let's suppose that we do it the other way. We assume that there is some function here. And for that function, we can in principle calculate the scattering matrix. Okay, and it will be a unitary scattering matrix because there will be everything will be reflected. And the question is, can we adjust that function to get the result that we have, right, with real n? It is possible answerable, right? But then one has to also check that in the multi-instanton sector also it works. See, once you have fixed n, right? Okay, I mean, multi-instanton sector also there is a one parameter, okay? Because there are different kinds of instantons. I mean, in this theory there is 1 1 instanton, 2 1 instanton, clear one instanton and so on. So for each of those instantons, there is an arbitrary parameter. And the question is whether by adjusting those parameters, we can mimic some nice function over here.
Yeah, I mean, it's sort of an inverse problem. I don't know how easy that is. I mean, to reconstruct a potential from
the scattering. Yeah, exactly. Yeah.
Yeah.
And it's also not completely clear that it will happen, because even for single instanton, for example, right, it's just not one scattering. I mean, you have n-point scattering on this side, right, given as an expansion in G string, and you have to make sure that all of those match, right, by adjusting the potential on this side. It's not clear that there can be a potential with this property.
Yeah,
but it's a question worth asking probably.
Yeah, I mean, this thing was sort of just in the spirit of a random guess. I mean, since bosonic string theory gives you a potential, which is qualitatively maybe of the kind.
So see, the bosonic string theory, right? The potential that it gives also has an unbounded on one side.
That is this right-hand side on this. So I'm just flipping the bosonic string theory potential.
Oh, I see. Okay. So you're saying symmetric.
No. I'm saying it's like here on this figure.
Oh, I see. Okay. So it goes up like this.
Yeah. It is just the bosonic string theory potential, but with a left-right flip. Because this is the unbounded side, which you already are kind of filling up. And then the other side is the usual bosonic string, this thing with a minimum and so on.
Yeah, but see, my feeling is that up to this point, you probably have to have the potential exactly as it is, because the instanton action is determined by this tunnel, this bounce. Right? And the instanton action you cannot do anything about.
Okay.
So the action associated with this bounce has to remain unchanged.
Isn't that just fixed by the quadratic part on the top? I mean, isn't it? Do you really probe a finite distance?
Yeah, you probe a finite distance, I think. Let's see. Okay, I mean, you probe a finite distance, there can be quantum corrections, but those are all computable. See, you have the D-instanton action to start with, right? Minus 1 over GS. And then there are quantum corrections to this action, which are given by basically vacuum diagrams. Okay? But those are all in principle computable in string theory. So I think you cannot arbitrarily change it.
Yeah, no, I'm sure you cannot arbitrarily change.
Yeah.
Yeah,
it's possible.
I mean, it's just if you had to guess something. I mean,
I agree.
It may not be completely well motivated.
I agree. Yeah,
that's all.
Shiraz also has a question, so maybe you can just take that before we go to the next talk.
Okay.
Shiraz, go ahead.
This is also following up on the matrix model issue, Ashok. Just intuitively, I'm probably not understanding well, but something's confusing me. I would have thought that the n for the single instanton was just determined by what was happening very near the bump. But
very near
the top, very near the bump, because the single instanton is just going through the top of the potential.
Not in top of the potential, right? Because the height is 1 over G string.
Yes.
Okay. So its single instanton is this tunneling.
Yes.
This bounce.
Yes. But if the potential was to turn up, that would be in these units very far away.
Yes.
Right. Because so I would have thought that just what's happening for the single instanton, that n for that would not be affected by what was happening very far away.
I think the point is that once it tunnels, right, there is e to the minus 1 over G string suppression, because this is a non-classical regime.
Yes.
Okay. This will be the classical regime, right?
Yes.
So suppose it turned upwards, right?
Yes.
Then you know that you cannot have a unitarity violation.
Yes.
And it will be shown up. It will show up at e to the minus 1 over GS order itself, right? See, in this region, there is no e to the minus 1 over GS suppressed, because this is classical regime.
I see. You're saying it doesn't matter how long it propagates. It'll go for a very long time, then hit and come back, but that's not suppressed.
Yeah, it's not suppressed by e to the minus 1 over GS. Exactly.
I see. And so one quick follow-up. I mean, you know, naively, you could just make any potential you wanted. Now,
Yes.
could it be that there's enough ambiguity in the string theory? Perhaps all your various ends in the various multi-instanton sectors and such like. So there's enough freedom here to construct absolutely any potential. That for every potential, there is a corresponding string field.
It may be possible, but that I think I doubt, because if you just look at the single instanton contribution, for example, right, there is only one parameter which you can take to be real.
Yes. But
Right.
then there are arbitrarily many instantons, each of which have their own parameter. Right?
But those will involve multi-instanton.
Yes.
Right? In the single instanton itself, there is one parameter but many amplitudes, right?
Yes.
And all those amplitudes have to be reproduced by whatever potential you do at the e⁻⁻ order.
Yes.
So it's not clear that anything will go, right?
I see.
You could reproduce, say, one amplitude, but to reproduce all the amplitudes
I see.
is not going to be easy.
I see. Okay. Thank you.
Okay.
Let's thank Ashoke again.
Thank you. I'll stop sharing.
Yeah. Gautam, could you please share your screen?
Yeah, hi. Am I audible?
Yeah, you're perfectly audible.
Okay, let me do that.
Okay, good. You can see the slides also. So the next speaker is Gautam Mandal from TIFR, and he will be talking about, also about C=1 strings, but quantum quench for fermions in 1 and 2 dimensions, lessons from C=1 string. Gautam, I'll tell you after 40 minutes.
Okay, thank you. Okay, so let me start by thanking the organizers. It's a great honor for me to be speaking at this conference in honor of David Gross, who is not only a great physicist, but has also made a phenomenal contribution to science building, not only in the United States, but also in various parts of the world, including India. So this talk is basically a progress report on work on thermalization that we have been doing for the last 6, 7, 8 years. And recently we are working on fermionic quench in 1 and 2 dimensions, in which it turns out that some techniques that we had developed in the discussion of C=1 matrix models, and later also applied to some other areas, have solved some problem which were not possible to solve otherwise. So let me go in steps. So basically, the idea is to look at non-equilibrium physics, in particular long-time dynamics of non-equilibrium states. There are some important questions which are so if you start from some particular initial state, is the cursor visible?
Yes, it is visible.
Okay, thank you. So does the system equilibrate? And if it does, what does it mean that the system equilibrates? Like in terms of what variables, which observables asymptote to some equilibrium values? And also, are there some special initial states which are required or is it for equilibration, or is it a generic statement? These are open questions in general, difficult to prove rigorously, but many results are known in bits and pieces. I will mention some of them. And the nature of the equilibrium. So the equilibrium may be thermal if there is only one conserved quantity, the energy, or it could be the GGE, which is the generalized Gibbs ensemble, which is characterized by infinitely many parameters, or it could have some memory of the initial state, like in the many-body localization systems, or it can have a defect density after the So we are going to talk about quantum quench soon. So after the quench, it can have a defect density as is known in the Kibble-Zurich transition. Okay, so and the rate of approach to equilibrium. So does it approach equilibrium exponentially, or does it approach by power law? We have found recently some interesting result in that also. So I will just flash them in one slide. Then the thing is just like in equilibrium physics, you have universality classes of critical exponents and so on. So are there some similar universality classes of relaxation rates? So okay, so as I said, so we will talk about quantum quench, a theoretically as well as experimentally popular method of creating non-equilibrium states is to do quantum quench. So you take a Hamiltonian, which could be a spin model or quantum field theory, and the idea is that the Hamiltonian would have some time-dependent parameter, and and the idea is to take it, start with a certain value, let's say G naught in this cartoon, and let's say we start with the ground state. It's not necessary to start with the ground state. You can start with some other more general class of states. And then you change this coupling constant from G naught to some G1. And we will find that if this G1 corresponds to some conformal, so the post-quench theory is conformal, then there are some general classes of results that we can prove, but that will be just mentioned in passing, because today we are going to talk about fermionic quench, which are of a different nature. So let's go. So what are the methods, okay, of addressing this issue of long-time dynamics? So the primary method remains numerical. Okay, among the analytic methods, so if the post-quench system is a conformal field theory, especially 1+1 dimensional conformal field theory, or it's a particularly simple system like a free quantum field theory or a ON model at large n in other dimensions, so d+1 space-time dimensions where d can be 1, 2, 3, etc. The thermal or GGE states as well as relaxation rates. So we are able to prove in these cases the statement of thermalization, and so we find indeed that some universal properties in this case, where it's a conformal field theory, that there are some universal properties of conformal field theory, the critical exponents which determine the relaxation rates. That is true of both the thermal case as well as the GGE. So that is to say, when there are the system is integrable, so there are infinite number of conserved charges. So I'm just summarizing these results before going on to the main topic of the talk. So very recently we found this result that if the number of space dimensions is odd, then the approach to equilibrium is exponential. So the relaxation is exponential like this. And if the number of space dimensions is even, then it goes like a power law. So this is something that we have been able to show in free conformal, the quantum quench in free field theories like a mass quench, or in some cases we're able to show this in ON models. Okay, so these are some field theoretic methods, and there are holographic methods like the quasi-normal decay rates of BTZ black holes, which are dual to 1+1 dimensional conformal field theory, or higher spin black hole decay rates. And in these cases, these are some of those rare cases in which both the gravity dual as well as the conformal field theory are easy to work with. And in case of the higher spin black hole decay rates, we found that the relaxation rate, exponential relaxation rate to the generalized Gibbs ensemble, these rates agree as a then of course more recently we have been working on another model in which the it's a simple model of holography where you can again work with the quantum mechanical system as well as the gravity dual with a great deal of simplicity and insight. And this is something that Spenta will talk about after my talk. Okay, so in this talk, we will discuss the application of phase-space hydrodynamics. So the so-called droplet method to the problem of quantum quench in Fermi gas. So it can be a Fermi gas or it can be a hardcore Bose gas, the so-called Tonks limit of infinitely repelling Bose atoms in 1+1 dimensions, as well as in a limited way in fermions in 2+1 dimensions. Okay, so these problems have experimental significance in cold atom systems. And we will find that the technique that we use here, in fact, we will borrow from the methods that were used in early applications in the context of C = 1. And later on, so the phase-space hydrodynamics is something that, appeared in this context, and later it was applied to the story of giant gravitons and also in low-dimensional super Young-Mills series. Okay, so this is the plan for the rest of the talk. So the statement of the problem. First, I will state what is the problem that we are trying to solve. Then the method that we are going to use, that's phase-space hydrodynamics for large N fermions, how it appeared in C = 1. And I'll mention 3 results. One is that the conventional hydrodynamics methods, which were tried by the condensed matter StatMech community to address the long-term evolution of these fermions in 1+1 dimension in particular, and they were stuck with the development of shock fronts, which caused conventional hydrodynamics to stop. So it could not be, so the time evolution could not be analyzed beyond the formation of the shock fronts. So we will cure the deficiency of conventional hydrodynamics by appealing to methods we have developed from C = 1. And we will go beyond the formation of the shock fronts, and we will in fact find equilibration. So we will find equilibration to generalized Gibbs ensemble, GGE. So we will hopefully have time to give you a little glimpse of a proof of this. And then we will also found universal relaxation exponents from the shape of the confining potential. Okay, so then we would, if time permits, we would talk about our ongoing work with condensed matter physicists on fermions in a rotating trap, 2-dimensional fermions in a rotating trap, so which are restricted to the lowest Landau level and have effective 1+1 dimensional behavior, and we can apply our methods even to them. So let's go. So the statement of the problem is the following, that experiments in a number of ultra-cold atom systems involve the following question. Suppose we have a system of non-interacting fermions or infinitely repelling bosons, this is also called the Tonks gas, which are suddenly released from a confining potential to free space, typically modeled by a periodic box, or to a different confining potential. So we have fermions in a trap. Okay, these are like a cold atom system which have some confinement. So that at the end the potential rises up. So it's a confining potential. So you can. So we are going to talk about just stopping that confining potential. This is done by switching off an optical lattice altogether, or to a different confining potential. So, for example, if you have a quadratic confining potential, so you go from kx squared to k prime x squared. So these are examples of quantum quench, and we are going to talk about some of these and properties that we have found in these things. Okay, so the problem is to find a subsequent quantum evolution of the state of the system. If we started, let us say, from the ground state before we did the quantum quench, and ask questions mentioned in the introduction, like thermalization or the lack of it, and relaxation and chaos, etc. Okay, so we are going to, in this talk, we are going to talk about thermalization and relaxation. The exact treatment requires finding. So how does the exact treatment go? Okay, which is mostly done numerically. So what you do is to, so these are, remember this is a Fermi gas. So the state is given by many fermion systems. So before the quench, it was the ground state. So that's the Fermi C. And you just follow that wave function which is like a big Slater determinant. And so after the quench, so if it is a sudden quench with like infinitesimal width of the time variation, then the or even otherwise, in fact, the fermion modes after the quench and the fermion modes before the quench are related by some Bogoliubov transformations. So apply the Bogoliubov transformations to the old Fermi C, and you get the new state, and you get some particular many-body eigenstate of the you get some excited state of the new Hamiltonian. So in case the quench is infinitely sudden, you have the wave function remains the Fermi C of the old Fermi C, and the idea would be to express that in terms of linear combinations of many-body eigenstates of the new Hamiltonian. This is complicated, and except in certain cases can only be done numerically. So we have done some numerical work also, and I will show you that for large enough number of fermions, our larger method of phase space hydrodynamics reproduces those numerical results. Okay. So let me tell you how it is conventionally described. So that is by using the usual Euler equations of motion. So when the number of particles is large, it is natural to try a continuum description in terms of the density, rho x of t, and the velocity. So local density and local velocity of the particles. The evolution of the particle density is and the velocity. It is assumed to satisfy the continuity and Euler equation of motion. So these are the well-known equations, and this is what was tried So the idea is that the configuration right after the quench, and you apply these evolution equations and see where it goes. Now, what happens is the following. Okay, when you apply these equations, is that this equation develops singularities when shock fronts appear, which are because of what happens is that the high density regions move faster, and high momentum regions move faster, and it leads to a distortion of the fluid, and soon enough it leads to regions where you have the gradient of the density going to infinity. Okay, so these are regions. So when that happens, our equations fail to tell us anything beyond that time. So attempts have been made to add some ad hoc terms to the Euler equation. So some additional pressure term, which is a phenomenological pressure term, basically to discourage the development of a singular derivative of rho. However, this do not solve the problem, and the time development beyond the shock cannot be computed reliably from conventional hydrodynamics, even with these things. So one of my current collaborators, Manas Kulkarni, as a condensed matter physicist, he was involved in these works. And also, of course, Damsky, who is another condensed matter physicist. They have done a lot of work in these areas. And the upshot is that this kind of phenomenological corrections to hydrodynamics do not work. So here's a particular graph which talks about the, what is this graph? So this is so there's an initial profile. Okay, so it's a double hill profile of the density like this. Okay, that is something I have called T less. And then I evolved this by the hydrodynamic method with the, let's say, with the correction term. Okay, if you do that, if you do that, then there is a time T naught at which the you see that the thing becomes vertical. It's a symmetric profile on left and right, so it becomes completely vertical at this time T naught. Okay, and therefore you cannot go beyond in the usual way. But then, of course, with this phenomenological term, you can try to go beyond. That is the time which I have called T greater. And you see that there are, these uncontrolled wiggles that appear here. On the other hand, the numerical calculation by talking about the many-body Slater determinants, that shows you some, the solid curve, which is clearly able to go beyond the thing. So the idea is to get some analytic method which can tell you the story beyond the shock formation. Okay, so the way we solve it is by using an exact large n description. It's exact in the large n limit. We'll also talk a little bit about the deviations from n equal to infinity. And so this was introduced in the context of the C equal to 1 model in some work that we did during 1992 to 93, which leads to phase-space hydrodynamics. So this led to the concept of phase-space hydrodynamics, which I will describe in detail next. Conventional hydrodynamics, in fact, appears as an approximation from this, which we'll try to explain, which breaks down at the time of shock formation. So in C equal to 1 also, the conventional hydrodynamics does appear from as a semi-classical description of the collective field formulation of Sachdev-Ye-Kitaev, which discusses real space density instead of phase space density. And in fact, it does suffer from the same problem of the evolution of folds and shocks. Phase space hydrodynamics is valid at all times and can address long time evolution and equilibration, as we will see now. Let me describe the method just a little bit. Devashish, please let me know when I'm going over.
Yeah, I'll tell you.
Okay. So consider n non-relativistic free fermions in 1 dimensions given by this single particle Hamiltonian, which is p squared by 2 plus v of x. Now introduce the second quantized fermion field described in terms of the first quantized wave functions, eigenfunctions phi n like this. That's the usual method. And this satisfies the second quantized field, satisfies the equation of motion, and the constraint, which is, this is the total particle number constraint, and this is the equation of motion. So these things are easy to derive. They just follow from the behavior of the single particle equations. Okay. Excuse me, these things should have been chi-n, because I have used chi-n here. Okay, all right. So now define the Wigner phase-space distribution operator, which has been used in many other contexts and have been worked on before. So this is called a Wigner phase-space distribution. So the idea is to track a particle in a phase space, which is of course not possible without the uncertainties. So it does take that into account. So here this is the phase space distribution for in terms of these second quantized Fermi field, and there are similar equations available for one particle wave functions of fermions also. Now the fermion path integral can be written in terms of a phase space density variable uxpt, which is an expectation value of this capital U in a W infinity coherent state. So now this is easier said than done. So you have actually to do a significant amount of work to show this. But I'll tell you the final outcome is that this little u satisfies the equation of motion, which is this is pretty much like what you would expect, that the time derivative is related to h comma u, but this comma business here is a Moyal bracket rather than a Poisson bracket, and the Moyal bracket is defined in terms of the star product here. So we are talking about the HU Moyal bracket. So Moyal bracket between two phase space functions, they are defined in terms of first defining a star product, and the Moyal bracket is the commutation of the star product, F star G minus G star F. All of these may sound complicated, but the part that I'm going to use is the n going to infinity limit almost throughout the talk, and it will be easy then. So what we are going to do now is to take, I'll come back to this slide in a moment. So we are going to take now the large n limit. So the large n limit will be something in which the number of fermions n goes to infinity, h bar goes to 0 in such a way that it is nh bar is equal to 1. Okay, so basically, the way you can work with them is that the in this limit you can see that the important states of this theory are the ones which are the highest occupied states, which are described by WKB under this approximation. This is some well-known fact. And so anyway, but you can do this, just formally also you can see what's going on, is that the Moyal bracket actually becomes a Poisson bracket. Okay. Because the F star G is almost like a product, but with an H bar order H bar term. So the product term actually cancels out between F star G and G star F. So that's the leading term. But the H bar dependent term that gives you the Poisson bracket. Okay, that is some this part is easy, so you can actually do that. And then you can also export this H bar from the left-hand side to the right-hand side. And in the limit that we're talking about, NH bar is equal to 1. So three things happen. One is that the star product, okay, the leading contribution of the star product is just the product, okay? So that gives you here U square equal to U. This gives you the integral of U is equal to 1. And in this equation of motion, you get Poisson bracket. Okay, so this is what I have written here. So the this is the equation of motion, which is now completely understandable. And u square equal to u, that of course is an important equation. So this basically has a solution, which is that u at any phase space point xp, u is either 0 or 1. Okay, so the phase space configuration actually therefore can be written as droplets. Okay, droplets in which the inside of the droplets you have u equal to 1, and outside of the droplets you have u equal to 0. So this is called a droplet representation. So you are automatically led to the droplet representation of fermion phase space configurations in this large N limit. Okay, so this is how the droplets look like. So here is a droplet, which is a simple one, in which if you draw, if you draw some, take an X, okay, take an X and draw a vertical line. Okay, so in my convention, X here is the horizontal axis and P is the vertical axis. So you take a particular X and draw a vertical line, it cuts the profile in two places, okay, P plus of X and P minus of X. These points are P minus and P plus. Okay, so this is called a quadratic droplet, okay, in which you have just two roots of this thing, P minus and P plus. Now it's easy to show, and which we will indicate how the quantities P plus and P minus get simply related to rho and V, and the equation of motion of UXP, which we encountered in the previous page, they lead to the Euler equation of conventional hydrodynamics if it is a quadratic profile. But soon enough, you should remember that the higher P regions, okay, they move faster, okay, and it develops these folds. And when you do develop these folds, then what happens is that you don't have just two roots. You can have, in this diagram, you have 4 roots. So it's like some P minus P plus here, and some P minus prime P plus prime here, and then the avenue which you took to derive the conventional hydrodynamics, they don't work. And this is, of course, a phase space profile. You can show that in the real space density profile also you develop when a fold happens, then the corresponding del rho del x, the x derivative of rho, that also becomes infinity. Okay, so that's what I have said here. So let me try to very quickly, let me try to tell you how the conventional hydrodynamics equations arrive. So here it is. So you have, let us say, for a quadratic droplet, what is the thing that it is equal to 1 if P is less than P plus and greater than P minus. So that's given by this bunch of theta functions here. And now the density, therefore, okay, so let us take this, infinitesimal strip here, drawn vertically from a particular X. And by our definition, the lower point is P minus and the upper point is P plus. So the density is just counting how many fermions there are in this strip. So basically, you take the U, which is the phase space density, and integrate with respect to dP. Now U is 1 between P minus and P plus and 0 outside. So therefore, you get P plus minus P minus. You have to take care of this pi and so on. Okay, so that's the density. Similarly, there's a momentum density that says rho times V, okay, where you integrate not U, but P times U. So at every point XP, you just add on to U this P, which is the local momentum of the fluid element. Okay, so what you get then is the PdP integral. and you get p square, p plus square minus p minus square. So you got rho v and you got v, therefore you get v, which is p plus plus p minus. The energy density, the phase space energy density, is simply the Hamiltonian itself, the single particle Hamiltonian. So that's p square by 2 plus v of x. Remember, that's what we are taking here. And the coordinate space energy density will be given by p square p square plus vx times p. The formula, which is like p plus cube minus p minus, sorry, excuse me, this shouldn't be p minus cube, and vx times p plus minus p minus, and which you can rewrite in terms of the rho and v variables. And Ritabrata, just give me 1 sec. Let me finish talking about this one.
Sure, sure.
Yeah. So the thing is that so then you know sort of everything that you need to know here is that the okay. Let me just claim that you know this. If you start from the equation of motion for u, which is given in terms of this you know theta functions of p plus involving p plus and p minus, then when you act these derivative operators to these things, so then there are delta functions and theta functions and so on and so forth. When you simplify all that, what you find is some local equation at the top, p plus, and some equation involving the p minus. So you get these two equations. When you take the minus of this, you get the continuity equation. When you get the plus of this, then you get the equation of motion. Yes, Ritabrata.
Gautam, you have 5 minutes.
Oh, okay. So maybe I'll take the question later if that is okay.
Yeah, okay, sure.
So therefore we get the equations of conventional hydrodynamics by looking at quadratic droplets. Okay, but as I said, you know, the droplet ceases to be quadratic soon enough, and the point is that we have to do something else in order to go beyond the shock formation of the shock front. So what we do is the following. So we realize that the U equation of motion actually is telling us the following. That so let me go to to another slide. So the U equation of motion is saying that start with the initial phase space droplet, where inside it is 1 and outside is 0, of course. So therefore only the boundary of you know the profile describes the droplet completely. So what I mean to say here is the following. So this slide says the following thing. So you look at all fluid elements. Okay, you can think of them as individual fermions, and you evolve them. Okay, this is the phase space point. So this is a diagram in phase space. You evolve this phase space point from starting from here to wherever it goes after a time t, and you do that for all the points inside this. In particular, you do that also to the boundary. Okay, so then of course, you know, this tells you that if this is the initial profile, then you can determine what the final profile is. Okay, and what you can show is that this, if you find your new profile u of xpt in this method, that in fact satisfies the equation of motion. So just to say that mathematically one says that uxpt is the same as u naught x prime p prime, where x prime p prime is the new point that you get from here, and applying the equation of motion for each individual fluid element is exactly equivalent to the equation of motion that you got here. Okay, so this is the technique that we use to be able to go beyond these shock formation, and we find that we are able to go beyond that time for all times. Okay, the result. So first of all, this is the way we solve the problem of the shock front, the singularity, and then the equilibration to GGE that happens, in this Fermi gas problems in the following way, that basically this the top here goes and hits this wall. So now what are we doing here? We are talking about free particles in a box, periodic box. Okay, so there is a little finger that appears. Okay, and then that goes and hits here, and then it's a periodic box. That means that this goes here and so on and so forth. So there's a filamentation that happens, and the long time average of that, okay, just becomes like this, which is the solid black here is 1. The U, and the white region, of course, is U equal to 0. And in the middle, the gray region is something that interpolates between 1 and 0. And that is precisely what you get if you independently compute this, the U variable, expectation value of UXPT in the GGE. Okay, so there is a...
Gautam, please try to wrap up now.
Oh, okay. So there is a nice math that you can do very easily by using the Poisson summation formula, which gives the mathematics of what I just said. And so this is, you can show this stuff. And so there's one thing which I must, so this is something that we had found first in the context of low dimensional field gauge theories, but this is actually a statement of the quantum quench, that if you okay, so let me just say that this graph says here, so this is a graph which shows agreement between numerical and n equal to 120 and n equal to infinity, which we just talked about. Okay, so the rho, as you can see that these two, so our method actually, for the infinite n method, actually, is sort of is in nice agreement with n equal to 120. We also have n equal to 200, so they start coinciding. Okay, so the other result that we have, we don't have time for that, is that you apply this method, okay, to also talk about relaxation rates. So in this specific cases, when the potential was x to the power 2m, that kind of potential to a free particle in a periodic box. Okay, so it goes as a power law. So it's some particular power law depending on that m. If you go from a box potential to a periodic circle, so to a larger box, then it's 1 over t. And if you introduce a cosine potential, blah, blah. So, okay, so that's t to the power minus 3 by 2. So this t to the minus 3 by 2 has been known for a long time, but our methods have provided a derivation of that. So much of these works are done with condensed matter people. Okay, so now we have been able to generalize this to 2 plus 1 dimensional fermions by using the fact that Landau level fermions effectively become like 1 dimensional. And okay, I don't have time to discuss this. So this is some ongoing work with Manas Kulkarni. So the Takeshi Morita is a string theorist, and Manas Kulkarni, Satya Majumdar, and Gregory Sher. They are condensed matter people, and hopefully we will be done in another 1 or 2 months. Okay, so the conclusion is that quantum quench dynamics we studied that in 1 and 2 dimensional Fermi gas. Large N limit leads to phase space hydrodynamics, which does not suffer from this problem of shock fronts, and allows the study of long time dynamics and approach to equilibrium, and we got universal relaxation rates. So we can talk about 1 over n corrections, don't have time, and possible double scaling, and some more ideas that we have about 2D model in which we can go to the higher Landau level. Okay, thank you very much.
Thank you, Gautam. Let's thank Gautam for a nice talk. Yeah. Ritabrata, please ask your question.
Yeah, means not anything conceptual. In the derivation you showed for the momentum density and the energy densities, so there shouldn't that the Vxt be p plus p minus by 2, from the derivation, it seemed like it should be the average thing because it's PDP integration, so there should be a half factor.
So the PDP integral is p plus square minus. Yes, indeed. Thank you, thank you. So there is
The average of.
Thanks a lot. There's a 4 pi here. There's a 4 pi here, and it will be given by p plus p minus by 2. Thank you. Thanks a lot.
Yeah.
Yeah.
There is a question in the chat from Panos, who cannot ask the question himself because of, well, he doesn't want to wake up others in the house. So the question is this, does your formalism, the phase-space formalism that you described, does it apply to only one body external potential, or its formalism is applicable in general to, say, something
that's the
Calogero model?
That's a very good. Yeah. I forgot to say in the open questions that's something else that we are also talking about, trying to do if there is a two-body interaction. The question. So let me repeat the question. The question is that we have discussed how to do Fermi gas, but how about it is if it is interacting? Now, amazingly, first of all, let me say that a lot of the cold atom systems, can actually be described by Fermi gas. And however, let us say if you have the weak interaction, how does this work? So the one possibility, of course, is that you have the aquatic potential like an ON model in this hard repelling Bose gas. Then presumably there will be some mean field approximation in which it can be reduced to a free gas again. But suppose there is a genuine interaction which cannot be reduced, then how does it work? So we have actually been trying to look at that also. And right now, I don't have anything definite to say. Thanks for the question.
Other questions? If Panos wants to follow up with that, he'll type the question. But meanwhile, if anybody else has a question.
I have one question, if I can ask.
Yeah, yes, sure. And go ahead.
So I think it's very nice talk, but one of the questions that I have is, can this one also use this formalism to compute a 2-point function, which is not equal time? So it's like a spectral function, or which can be directly measured, or say the statistical function, which is the commutator instead of the anti-commutator. And the spectral function, especially, we know satisfies this very nice sum rules and has very good physical interpretation, is positive definite if you do, things like that. It can also be measured. Yeah.
Indeed, it can be done. So, so in this Fermi gas problem set, because I have not made slides for those, but indeed it can be done. Yeah. So 2-point functions of density variables, not just the expectation values of rho and v, but also 2-point functions of rho can be computed.
Okay, in this case, I have a follow-up. So there are many field theories, ways of understanding thermalization, especially in ON models, done by Burgess group, if you're aware of it. When they have, so what they study there is something interesting. They study the statistical function and the spectral function, right? And if there is a thermalization, they start do it only for pure states. If there's some effective thermalization, there'll be some emergent fluctuation dissipation relation, right? This KMS condition will come out, right?
I know what we're talking about. So these are some of the things that we also wish to study. So far, however, we do have the delta rho, the 2-point function of delta rho, which is rho minus rho expectation, the 2-point function of that. We have some specific results for them. But whether we can, this is something, thank you for mentioning this. This is something that I'm aware of, we are aware of, and we are also, we also wish to do this. Thanks.
Thanks, Gautam. Amazing talk again. Thank you.
Thank you.
Is there some other question? Gautam, can I ask a wild question? Matrix model originated from understanding nuclear spectra. Now, your phase-space droplet method, can one go back to nuclear physics and answer any question about thermalization in any of these collision experiments or anything?
I think so. I think so. That's a very good question. I didn't think in that direction, I must admit. But basically, it's a Fermi gas, and maybe it's a Fermi gas in a bag or something. I mean, I don't know how. Yeah. Of course, you know, it was very phenomenological, as you know. I mean, it was just supposed to reproduce the spectral distribution. How much more dynamics of the, I mean, the you know, the density of nuclear energy levels was supposed to be reproduced by, you know, as if the Hamiltonian was a random matrix. But yeah, I mean, my knowledge here is rather limited. I don't know whether they have got any further dynamics than just this. But it is also true that some of the, you know, some of these methods, I mean, the shell picture and so on and so forth. I mean, there is a Fermi ball picture, which seems to work also.
Yeah, so Rajesh has a question. Somebody's probably giving a lot of feedback.
Yeah, some
Hello?
microphone.
Yeah, Rajesh,
Yeah.
could you?
Just a very quick question, Gautam. So this these shocks and these folds that you showed, in the context of, I mean, string theory, where you have these sort of droplets in LLM type of geometries, and you also have something similar for the in terms of looking at weakly coupled Young-Mills also. So is this shock, can it be associated in some way with the formation of a black hole or something like that? Because there was this something I had done with Shivankar long ago. We had looked at, in terms of the holonomies, you know, this thing of this deconfinement transition, but if you look at the holonomies, and you can get a phase-space picture there, and the black hole and the thermal ADS, somewhat like in the LLM case, they were kind of, there was this sort of this fold that formed when you have black holes. So I was just wondering whether there's some intuition like that you may. It's a little bit vague question.
Yeah, no, that would be great to have, but you know, as you know, the LLM geometries, they don't quite describe black holes because in that they are not. But of course, there is this what is it called, the superstar or something, which has always you know. So these are some kind of singular black hole configurations which you can. You know, consider, which do not have this U, the phase-space density variable that appears in LLM geometries. So you know, that has to be 0 or 1 for smoothness of the LLM geometries. Okay, yes. But if you relax that condition, then you get this so-called superstar configuration, which do have properties like a singular black hole. And so there has been some work related to that. But what you were asking is about the you know, genuine garden variety black holes with holonomies.
Yeah, so actually that's what I mean. We were, when we did this work with Shivankar, we were inspired by the LLM kind of picture, but it was independent of it. And there we were trying to apply the same phase-space picture, actually the similar formalism cropped up. If you just try to understand this, you know, this the deconfinement transition at weakly couple Young-Mills of Shiraz and Ofer and all that. If you try to understand it, there's a phase-space language in which you can understand it, and the phase-space droplet picture of the Thermal ADS is sort of like without the fold, and the phase-space droplet picture of the black holes and so on are with folds. And in fact, Shubhankar and his students have been sort of developing this a little, quite a bit further in various different cases. So this sort of like a phase-space picture in unitary matrix models.
So I see. So we have actually talked about this phase transition, from ADS to black hole phase transition, using this phase-space formulation for the Gregory-Laflamme transition in this. But I would be very happy to talk talk with you about this development.
Yeah, this fold dip is sort of very, this thing that somehow maybe the shock is somehow related to a black signature of a black hole or a horizon or something like that.
Well, time is short, but Panos pointed out that it's related to Rajesh's question, that the point that he made is related to that for black hole formation, you will probably need this interparticle interactions like in Calogero and so on. And Shiraz has a question. Shiraz, could you please make it quick?
Sure. Just vaguely along the same lines as Rajesh's question, or maybe just a vague comment. Another place where folds could develop is in fluid gravity. You've got these black brains and they're wiggling around, and that gives hydrodynamics. And if then they developed a fold, that would signal a breakdown of hydrodynamics, would go outside the fluid gravity regime. And okay, but it's a sort of thing that I find interesting, and I don't know if it's okay. Is that in this large D way of looking at things, the membrane can bend over, and that whole folded description can be described in terms of some sort of upgraded hydrodynamics. Hydrodynamics that lives along this large D membrane rather than the fluid gravity membrane. So I suppose I was just wondering whether there might be some sort of hydrodynamics that lives along the local shape rather than the projected shape in your setup. Just a vague question. We can talk about it later.
Yeah, that also sounds interesting. Let me just say what the resolution that we have used here is precisely this, that you follow the fluid particles along the boundary of the droplet. Okay, so that is always a smooth motion, right. And that is what allows you to go beyond the folds and so on. So your remark seems a little similar to that.
Yes, and, I think. Yeah. Thank you.
Okay, let's thank Gautam again. Next speaker is Spenta. Spenta, could you please share your screen? Hi, Spenta, can you hear me? Yeah, okay. Yes. So next speaker is Spenta Wadia from ICTS Bangalore, and he will talk about black hole formation in the SYK model and 2D gravity. Over to you, Spenta. I'll tell you 5 minutes before your time.
Okay, thank you so much for this kind invitation. And it's an honor to talk in a meeting which is organized to honor David Gross. So before I begin my talk, I just wanted to recount a few memories. So David Gross, as Ashoke and Gautam preceding me today mentioned, not only a great physicist, but also has contributed a lot to growing science, especially in the developing world, in India and also in China. So my own association with David Gross goes to about 1976, when he first came to lecture on the Gross-Navier model at City College, where I was a beginning graduate student. I don't have those photographs, but in these times of COVID, I could assemble a few pictures of David's association with India. And the first picture, of course, is a picture in the almond grove of the TIFR Mumbai campus during Strings 2001. You all recognize the three gentlemen there. And so that was a great meeting we had, organized mainly by Atish, Sunil, and myself. And it was David Gross who basically said, let's get Stephen. So it took a bit to get Stephen, but he came, and we have this magnificent meeting there. So
interrupt you. You
yes.
are using this. You are using a portrait format, so the slides are slightly small. Could you leave the full screen mode or something and make it wider?
Oh, I see. Okay. Sorry. Just 1 minute.
Maybe just use full width display.
How about this? Shall I share again, or?
Yeah, I didn't change anything here.
I understand. Just 1 minute. Please give me a second. I'm very challenged in all these matters. Is there some thing I can do?
What are you using?
I'm using my iPad, and it's Good Notes. So I'll tell you what I'll do. I'll just come out of it, and then I'll go back. Sorry about this. I think I know what the problem is. So can I just please do that?
Yeah, sure.
How about this?
No, it's still the same.
Oh, I see.
You just choose the full width, or if you're keeping it in portrait mode, if you turn it over to landscape, it may do it automatically.
Oh, I see. Okay.
Or Spenta, just use your hand and expand it.
Yeah, this is better.
Yeah, much better.
This is better. Okay.
Yes.
Yeah. Okay. Better? All right. Sorry about all this. So, I just wanted to revive some memories of David's association with India. And this was Strings 2001. And then, of course, David was so instrumental in supporting the creation of the ICTS. And here is a picture of David with Professor C.N.R. Rao and Dr. Srikumar Banerjee during the inauguration of the laying of the foundation stone of the ICTS. And not only that, he's one guy who actually came and visited and wanted to see the plans, wanted to make suggestions. And here you find him discussing the plans with Avinash. I think it's Avinash, right? And then we had the inauguration of the ICTS campus, and David planted a tree, and Vijay after that, and all those trees have really grown. And David, you should come again. It's not only that, but his association with us continues. And here is a photograph of ICTS at 10, and he is still with us. So with these few words, let me begin my talk. So David, I hope you are there and not gone to sleep yet. Okay, so this work, which I would like to present, can I just change it now? It's maybe better. Is it okay now?
It went back to the same portrait mode, which makes it slightly smaller and difficult to read, but if you're more comfortable with that, it's okay.
No. Okay, let me try something. I'm so sorry about these things. Okay, so I'm going to talk about this work, which was done in collaboration with Avinash Dhar, Advait Gaikwad. I have boxed him there because he's one of the very outstanding students who contributed a lot to this program. And there's also some work in progress in which he's made very important contributions. Okay, so all right. So the black hole information problem is with us since 76 since Hawking's paper. And subsequently, there have been many sort of theoretical developments trying to understand this and solve this problem. And some of the methods that were developed by us have been described by Gautam in the last talk. So most of this method that he talked about was developed to understand the two-dimensional black hole in string theory. But it didn't work out for reasons which I may allude to. But nevertheless, useful. All these things are useful in other contexts also. So I just wanted to turn the question a little bit around that black hole formation is also a version of information loss. Because you would be starting with some pure state, and it evolves into a black hole, which is classically described by solutions of Einstein's equations, and its quantum mechanics essentially is described in terms of a mixed state or a density matrix. Okay, now in the ADS-CFT correspondence, this process essentially has a dual. So you start with a corresponding state in the dual theory and let it evolve, maybe after a few quantum quenches or even without that. And it asymptotically will reach a thermalized state. And one of the reasons why the SYK model is very important is because this process is actually very explicit, as I will discuss later in the talk. So precise formula, we would like to make a precise formulation and calculation of this process in the SYK model in the context of beginning with a pure state and always continuing being part of a pure state. So before I do that, let me just remind people about the SYK model. The SYK model is a model of random fermions, sort of similar to random matrices, but it has extraordinarily important properties. So the low energy effective action or the hydrodynamic action of the SYK model is given by this formula. This is the famous Schwarzian. And this model exhibits chaos, unlike the old C=1 matrix model, which is the reason why it couldn't describe black hole physics. And it has microstates, explicit microstates, and low energy pure states, which are easy to construct. So it is something you can calculate with. And it's dual to ADS2 spacetime. Okay, so this is a very fantastic thing this Kitaev, Maldacena, Stanford, Young, and many others have developed. All coming from condensed matter physics. Okay, so the quantum mechanics, SYK model is essentially the quantum mechanics of n real fermions with all-to-all random interactions. That's the key point, the all-to-all random interactions. And it's described in terms of this Hamiltonian, which has a Gaussian random noise. And that's the model which people have studied. And what we want to study is essentially a perturbation of that model with a very specific Hamiltonian, which was invented by Kurkulu and Maldacena. And this operator is dimension half in the infrared because the fermions are dimension 1,4. And so it's sort of relevant. And we want to study the dynamics of this Hamiltonian system for black hole formation and evaporation. Okay, so what is the Hilbert space? Hilbert space of this model is very simple. So let me, maybe I've discussed it later. So let me just, this objects over here, the spins, are just presently take plus or minus values in like in a Ising model. Okay, and this specifies a microstate. I'll explain this later to you. Okay, now before you all fall asleep, let me tell you what the main results are, at least some part of it. The SYK model provides the simplest holographic model that enables a computation of the process of black hole formation in the bulk. So we compute the evolution of pure states through two quantum quenches. The first quench of sufficient strength extracts energy, and the space-time horizon disappears. It's a result of Kurkulu and Valdesena. Does not violate the second law of thermodynamics because you're extracting energy or pumping in negative energy. And the second quantum quench pumps in energy that leads to black hole formation. And what we can calculate explicitly is the temperature of this asymptotic black hole state. And it has this very interesting chopped form with this exponent half. Okay, so this is the result. And then I will also subsequently describe ongoing work, but there is no conclusion, so I have not put it here. So microstates of the SYK model. So as I said, you have real Majorana fermions. This is the commutation relation. And basically these are, up to a constant, the usual gamma matrices in higher dimensions. And okay, so this is the representation of the gamma matrices. And I don't want to elaborate all that, but this operator, which I talked about before, the Hamiltonian, essentially is proportional to this guy, and it has these eigenvalues plus or minus 1. So the Hilbert space is spanned by a large number of 2 to the n upon 2 orthonormal states, and this is the Hilbert space. So, okay. Now, I think the merit of doing all this is to understand the connection of the physics of microstates with thermalization. And for that, what we do is we take these states, these BS states, which are essentially random spins, plus, minus, etc., and make a low energy projection. A low energy projection means L is very large. It's just half the temperature. And you get this whole family of over-complete states, but they all are at low energies, means expectation values of operators in this type of states can be understood in terms of some hydrodynamics, as we will see. Now, Valdesena and Kurkulu observed a very important fact. And they observed that there is a subgroup of SON, which is as follows, that it maps even fermions into minus of the even fermion and leaves the odd fermions alone. Okay. So this you can show is a subgroup, and in fact, the spin operator, which is just a multiplication of subsequent SYK fermions, like psi of 2k minus 1 times psi of k, clearly is odd under this flip symmetry. And in particular, the important point actually is the fact that any state of the Hilbert space of the SYK model lies on the orbit of the flip group. Means you start with plus, and you can create any state actually by the action of the flip group. So this important point. Now let's come to thermal properties. So this is a definition that if you want to compute the average value of some operator in this state, and you sum over all the spins, then clearly you are computing the trace. I mean, you can prove this from here to here. This is the thermal partition function. Okay. Now, it's incorrect to say its definition. Sorry about that. Now, the important point is that if this operator is flip invariant, then this summation over here really drops out. because just the full orbit of the flip group is not important because of the flip symmetry. And therefore this partition function, thermal partition function, can be evaluated as an expectation value of pure states for any microstate BS. Okay. Now, flip invariant operators cannot distinguish between microstates. That's the point, actually. So if you want to see microstates, you got to turn on operators which violate this symmetry. Okay, that was the real motivation of Kurkulu and Maldacena. And you can, I have just some two formulas over here for your information, that the partition function is essentially the norm of this BS states for any S. And again, you can compute the thermal 2-point Green's function in Euclidean time over here, given by essentially, again, an expectation value in pure state. It's quite remarkable, actually. So in a sense, the system for certain operators immediately thermalizes. I mean, there is no waiting or anything. Okay, so that's a property of the SYK model, which is quite interesting. Now, what is our, now let me set up the calculation actually. So I said that this is the SYK Hamiltonian. We want to start with a total Hamiltonian, which is this one, plus a perturbation actually. So I'm not going to really do a lot of details because I mean, I don't have the time. So this is the perturbation Hamiltonian. This is the spin operator I was referring to before. You can see that the square of this operator is 1 and its eigenvalues are plus or minus 1. And these are the eigenvalues of this operator. Now, the important point here, and this is a point that was made by Kyriakos Papadadimos and Surat Raju, that we are looking at an operator over here which is state dependent. So these numbers Sk are the same as the numbers Sk that specify this state. Okay. So I just wanted to make this comment that the SYK Hamiltonian is obviously flip invariant, but this object is not. Okay. So now we want to compute things. So in order to compute things, you need to set up a formulation. And so I want to firstly talk about these two wave functions. So this is the Schrödinger picture of some state at time t equal to 0 evolved by the full Hamiltonian. And this state is the one that you get by simply evolving by the SYK Hamiltonian. So full Hamiltonian means SYK plus the perturbation. And the main object of our study is the overlap of these two states. Okay, so we now that we have the object to compute, so now we can do the calculation. So, all right, so this is a standard type of, not so standard, Schwinger-Keldysh type of computation, which is done in very great detail in our paper. And there are several ways of looking at it. This is my own starting point. And all said and done, and this actually requires quite some doing, that this model, this problem over here at low energies is described essentially by the SYK model path integral with an additional interaction. So the original hydrodynamics of the SYK model described by the Schwarzian is now modified by the introduction of this new term. Okay, and this term plays a very crucial role in whatever I want to say. All right, so delta in our problem over here is 1/4, okay, because we are working with 4 fermion model. So this object is f prime to the power of half. Now, what has all this got to do with gravity? So very quickly, since I think I'm running out of time already, is that what about the bulk dual of the SYK model at low energies? Okay. So there are two formulations. One is the one that you arrive at by looking at the coadjoint orbit of the infrared, the Virasoro group of the SYK model. So the SYK model is not conformally invariant. It's a very important point. And it's only for that coupling constant j equal to infinity, it is conformally invariant. But for any finite but large j, there are deviations from conformal symmetry, which are precisely described by the Schwarzschild action, which I mentioned before. So anyway, what is the dual of this near conformally invariant theory? So if you work, you can actually construct the gravity theory almost in the bulk by looking at the co-adjoint orbit of diff 1 upon SL2R. So I have just the result, which I don't want to. We did this model in order to derive the ADS-CFT correspondence in this very simple model. And it's amazing that the quantum mechanics model essentially reproduces a theory of gravity in 2 dimensions. The only thing we couldn't really fix was the value of the cosmological constant, but perhaps with some very hard work, it's possible to do that. Okay, now there is another formulation, there is another dual which people use, and this is the Sachdev-Ye-Kitaev gravity, which everybody knows what it is. It has a very important dilaton field with a certain boundary condition, and it arises from the S-wave reduction of a near extremal charge black hole. So it enables you to make a connect with higher dimensional geometry. However, what is important, and this is very nice actually, that in both theories, whichever gravity theory you work with, the Polyakov theory or the Sachdev-Ye-Kitaev, there are no propagating degrees of freedom, and the only physical degrees of freedom are large diffeomorphisms at the boundary. By large diffeomorphisms are defined in terms of a map of tau with some real number, real parameter, to a space of functions with the proviso that the Jacobian with the f prime, the derivative is positive, or it can be 0 at most. Okay, so if you work out near, just a little calculation, near the boundary of ADS2, what this diffeomorphism looks like, it has this very important form. So the time essentially becomes f, as we expect, but very importantly, this z coordinate is proportional to the derivative of f. Now, what is the consequence of this? So this has a very profound consequence, actually. It's the following. So let me take this slide and just draw pictorially. This is the Euclidean version. This is the Poincare disk. And some region is cut out over here with a certain boundary. And we are talking of the diffeomorphisms of this boundary. And the Lorentzian picture is over here. And the important point which I want to make is that in Poincare coordinates near z equal to 0, as I mentioned before, the diffeomorphisms essentially act like this. So now you see that if f prime is equal to 0, okay, for some reason, then zf is equal to 0. Means the space-time ends. And an observer over here, therefore, will stop receiving signals from here. This is a very simple and a beautiful way of characterizing the appearance of a horizon. And this is all very beautifully explained in the work of Kurkulu and Maldacena. Okay, so this is the connection of the reparameterization symmetry and the vanishing of the derivative of f and the formation of a horizon. Okay, so this is just some other picture which I have just drawn, but basically it's a space-time picture in which you have a very heavy state over here, and the resulting geometry is more or less the same like a Poincare patch in which there is a black hole. I don't want to explain all this because it will take me too far away in time, but these pictures you will remember. Now let's get back to the SYK model. Okay, so I already explained to you this Keldysh contours, and I mentioned to you that the effective action has this additional term. All right. Now, what we do now is that we would like to evaluate this path integral actually in the semi-classical method. And since the initial state at t equal to 0 describes a black hole because it's a finite temperature system in the boundary theory as well as in the bulk. It's very simple over here, how to go from 0 to finite temperature by just a conformal transformation. So the solution actually that is characteristic of a black hole is precisely this map of tau to f of tau given by this tangent hyperbolic function. And beta is the temperature of the black hole. But now, we are describing everything as a pure state. So it's just some parameter of the initial state of the system, okay? Now we make a change of variables because the integration over f is rather complicated because it has this measure of the diffeomorphism modded by SL2R. But with this particular change of variables, which was done by various people, this is a flat measure path integral. And you have a very simple Hamiltonian system that emerges. The Hamiltonian system has a peculiar potential. It's peculiar because of the following property, that if epsilon is negative, okay, the potential is like this. Now this potential only has scattering states, so its energy eigenvalues can only be continuous. Okay, so that's why people say that this is not a good Hamiltonian system. But this is a simple point. And the motion, if you have some energy over here, then the particle simply goes back to minus infinity in phi, and the exponential of phi just goes to 0. And this means basically that f dot hits a 0. So all trajectories like this, as per our previous discussion, describe black holes because they describe horizons. Okay, so that's the point which I wanted to make. Now, because I'm using this horizontal view, every page is like this. Okay, so this is once again the picture which I wanted to draw, that f dot equal to 0, which happens at asymptotic infinity in time, simply translates into the fact that a horizon is formed over here. Okay, all right. Now, what about the parameters when epsilon is positive? When epsilon is positive, clearly this potential has very different properties. It's topologically different properties. Firstly, that it hits a 0 over here. Okay, the potential always has a 0. It always has a minimum for any value of epsilon, more or less. This is the shape that is true. And so the issue is that if you want to go away from the black hole phase, then you just have to go below the negative energy into, you sort of, start with things like this, which are above E equal to 0, and then just come down over here. Okay, so now this is the remarkable result which was derived by Kurkulu and Maldacena, and this is really which I felt was very, very exciting, is the fact that for a specific choice of that Hamiltonian of parameters, it is possible to describe a geometry in which there is no horizon. And there is no horizon because in this potential problem, there is a bound state. If there is a bound state, the field phi is bounded. If it is bounded, it means that it never goes to 0. Therefore, f dot is never 0, and therefore there is no horizon. So this is the first quench which was introduced by Kurkulu and Maldacena, in which they were able to describe a deformation of the SYK model in which the geometry doesn't have a horizon. Okay, so that's great. Why it is great, I will say, because you start with a geometry without a horizon, and then you start building once again a geometry with the horizon, and that's precisely the black hole formation, which I will now discuss briefly with you. How much time do I have, Debashish?
Sorry, I was muted. You have 12 minutes or so.
Okay, I'll try. Okay, so the main lesson over here that we have learned is that by tuning the quench parameter epsilon, we can pump out or put in energy into the system. Okay, and if you pump out energy, means if you put a refrigerator there, then the horizon goes away. And if you pump in energy, you can form a horizon, depending on whether the classical solution exhibits these two properties, whether the Jacobian is not zero or whether the Jacobian vanishes. Okay, so this is the main lesson which I wanted to sort of get across to you. And now we can having understood the physics of this, we can really do a calculation. So what we did is the following, that we took the quench parameter. So there's a critical value of the quench parameter below which you'll always be in a black hole phase, because you'll always have a horizon geometry. Above this critical value, the horizon goes away. So you start with above, and then you can actually go slowly over here. But for calculation complexity, is greatly simplified if we essentially use a simple function, which is a constant, doesn't vary at all till it gets over here and then it jumps down. So, the point I'm trying to make is that this object over here has a hidden time scale of its own. That depends on me. So if it moves very slowly compared to the typical time scale of the SYK model, which is set by this parameter J, the dimensional parameter J, this need not be really a constant, but can slowly come down over here. Okay. Now, what does this mean actually? It means in this potential picture, let's start the trajectory in which the particle is at the bottom only. I mean, I'm at so low energies that I'm not over here. I'm not performing any periodic motion, but I'm just here. It's a state. Now, important point is this is this energy is negative, and actually that's very important, because in order to now create a black hole, I have to pump in enough energy that this state essentially goes over here and sits on this potential, and then the particle flies away. So this is the idea. It's a very simple point, actually, if you think about it, because there's a huge formalism that brings you down to simple undergraduate physics, actually. And the detailed solutions of all this are worked out in our paper. You can do everything explicitly and exactly. That okay. All right. So this is the space-time picture. I took this picture from somewhere. So this T of U that is over here is actually my F of T, okay? Sorry about that, but it was a nice diagram. So what is going on here is that this is the state we started with at time t equal to 0, okay? This is the state of the SYK model, okay? Then we turned on a certain quench over here that was done by Kurkulu and Balasena, and it went a certain distance. And then we put in we pumped in more energies over here, and we changed the trajectory of this particle. See, f of t in some sense describes a particle, and we change its trajectory to come and hit a 0 over here. So that is the formation of the black hole, actually, which you can only say it's a black hole after the whole event has passed. And this is a property well known, that you can only glean there was a horizon once you have reached here. Okay, so, and you can follow this whole dynamics explicitly, and I think that's quite important, because it's hardly possible to do such explicit calculations in more difficult models, but this makes the point. Okay, so now we look at the asymptotic solution that is above the E equal to 0. And you can pull out essentially this parameter C over here. all right? And this parameter C basically can be related to the temperature of the black hole just by looking at the asymptotic formula for the tangent hyperbolic function, which describes the black hole at real time. And you get this very simple but exact formula. And this formula is this particular what shall I say, particular shape that is controlled by an exponent which is half, and it tells you that there is a critical value of the parameters that you tune to make a black hole below which the black hole cannot form. Okay, so this is the Choptic type scaling law. So this ends the first part of the talk, and yeah, if there are any questions, I can take them, even though I'm running late at this point. Okay, seems not. So let me just now present to you the problem of the modeling of black hole evaporation. So this is work in progress, but I thought I'd just spell out the formulation of this problem. And this technically turns out to be a very difficult problem, but I think we'll all get there at some point. So what we do is, see, because you cannot describe evaporation in ADS2, because we all know that a black hole cannot evaporate because the radiation will reflect from the boundaries. So we have to introduce an additional system, and that is the bath, which is very popular in various recent very important progress which has been made in computing the page curve. We'll hear from Raghu Mahajan on all these new developments, I think, sometime during this week. Okay, so you therefore augment the system. So this is the SYK model. This is the Hamiltonian perturbation, which I talked about, the relevant Hamiltonian perturbation, which kicks in at time greater than 0. And this is the simple bath Hamiltonian. And this is the interaction. Now, if you have a scalar field in the bath, I mean, how will it be able to exchange energy with the SYK model? So for that, one had to invent marginal operators, 4 fermion operators in the SYK model. And this was beautifully done by Advait. And here is the construction, actually, that what you do is basically you lay out all your fermions on this one-dimensional lattice. And then you form M bins, capital M bins, when M is a very large number. And in each bin, you put, you make semi-bins in which NF semi-bins in each one of these big bin. And in each one of them, you put 4 fermions. It's a very beautiful construction, actually, and it's has very interesting permutation symmetries. This interaction is permutation invariant. And here is the operator. It's a dimension 1 because each one of them has dimension 1/4. And so you need these operators to couple to the bath. You can't just couple anything to a bath like this. All right. So once this is done, once again, what we have to figure out what to compute. So we'd like to calculate the expectation value in pure states, pure initial and final states of this operator, actually. And this is the operator phi hat, whose classical value is the Liouville field phi of the SYK model. And okay, so you take this Hamiltonian, the full Hamiltonian, and evolve the initial wave function. Okay. And what is the initial wave function? That's the point. The initial wave function
5 minutes, sorry.
Yes, I'll finish in 5 minutes. Is BSL, the old friend that we worked with before, but there is a Calabrese-Cardi type of squeezed state or something, which describes the bath, the initial pure state of the bath. both these states are described by some parameters, small l and capital L, which in the thermalization limit essentially translate into inverse temperature. So this is the inverse temperature of the bath, and this is the inverse temperature of the black hole. And for our purposes, capital L has to be very much larger than small l, okay? Because a hot system will go over and evaporate into quanta of the cooler system. Okay, so you set up this formulas. So this is a very typical Keldysh type of formulation, and well, here it is. You want to compute this, which is this, and it's schematically given by this contour that you start from here. This is the bath, and this is the SYK model, and they are interacting all the way. These things interact. I show you that there is an interaction, as I have indicated, and at time t equal to capital T, which is very large, I want to see what is, for example, the expectation value of exponential of phi. Okay, does it go to 0 or does it not? That's the key question. So we set up this whole formalism to do that, and ultimately you arrive at Keldysh type of effective action, which is given over here. And I've just described this Keldysh type of effective action because there are two contours, so you have two fields. This is the exponential of phi, this is the exponential of phi bar on the other contour, and so on. And so these are the different kernels which you get in the Keldysh formulation. And the important property of this kernel is that it turns out to be something like this, which I believe will be important in solving this problem. It has this particular behavior, t plus t prime and t minus t prime. Now we very carefully need to consider the saddle point method in the Keldysh formalism because there are two fields, so we have to understand this. We've just begun doing this. And ultimately, we hope to prove either by numerical methods, which looks very difficult, or by qualitative theory of differential equations, integral equations, qualitative methods, that the asymptotic solution for very large T, capital T, is such that exponential of phi at capital T does not go to 0, which means that you don't have a horizon. That means the black hole is gone. So this problem becomes very difficult because we have integrated out the bath completely. You see, all those quanta are integrated out. So you have an effective theory of the SYK model with very complicated propagation kernels. Okay, so this is more or less the end of the talk. So in conclusion, we presented an explicit example of black hole formation in the soluble SYK model. And secondly, we have precisely formulated the black hole evaporation path is at a lower temperature than the black hole we expect. No black hole in the final state. And this is a hard problem, but we will get there. And we will get there because even if you fall down, you can stand upright again. It's a very favorite picture of mine of David. So thank you very much for your attention.
Let's thank Spenta again. Yes, thanks Spenta for a nice talk.
Thank you.
Questions? There is a question from Haridas. Haridas, would you like to unmute yourself and ask the question? Well, I don't know if he's there, but he had typed it quite early in the talk. So let me just read out the question.
Okay.
The singularity theorems of Penrose were conditional on the assumption of trapped surfaces forming. can your approach prove that trapped surfaces are actually formed instead of assuming their formation?
Well, I think we can actually see the horizon is formed, right? From the dynamics of the reparameterization mode f of t. So one point which is important in, let me just mention, since you mentioned Penrose, is that in all these calculations, you are not encountering any singularities as yet in the large N limit. This might be an important thing for trying to understand the ADS-CFT correspondence for higher dimensional black holes. There are singularities, discontinuities in the 2-point function, for example, but they are rather mild singularities, let me say that.
Yeah, I was actually going to ask you that in this approach, so if I understood correctly, the thing you want to compute is that the final state of the SYK model would be some zero temperature state or some state without a horizon, like it would be cold at the end of it. But would it allow you to read off like the properties of the interior of the black hole, which would now be in the past, you know, of the when you're way far in the future, the black hole has completely evaporated. There is still this interesting region which is left, which is this, you know, behind the horizon that used to exist, and the singularity is there and so on. Can these methods teach us something about that? Let's say in falling observers and stuff like that.
Yeah, I mean, so this is a very lower dimensional model, so I do not have that very good picture. But one thing is there, that the dynamics of f of t is there from time t equal to 0 to very large times, t equal to infinity. So you have the full history. Now, your question is about the mapping of that history into the
deep interior, let's say.
Into deep interior. So I don't know the answer. This is a very important question. The questions of mappings of what happens on the boundary to what happens in the bulk. For this, I don't know the answer to this question. Even if you know the boundary completely, you need to know that map in order to get some information. Yes. Yeah.
Thank you. Thanks.
Yeah.
Debashish? Can't hear you.
And if you want to ask a question, just go ahead. I mean, we'll see what happens.
Spenta, I want to ask something.
Yes, please.
Firstly, yes. Now I can hear you, Debashish. You had we couldn't hear you for some time. Thanks for the amazing talk, Spenta. I want to ask you about something. Is that we also found a similar solution when we coupled a particle at the boundary self-consistently with an NADS2, but we didn't study black hole formation though. We studied, and we also found a very interesting non-equilibrium phase transition there. So interestingly, the total energy of the particle, the kinetic energy of the particle and the black hole mass is conserved, and then a system evolves, right? And what we found is that the black hole evaporates, like in your case, in this, or like in one of your possibilities that you have, depending on the quench. But there is something very interesting that we find is that when that the final state, the SL2R charges start blowing up exponentially, but the Casimir goes to 0. Yeah, and this blow up of the SL2R charges remembers something about the initial condition. So it somehow remembers where you started from. So is this some kind of similarity? Can be, is there some kind of remembrance of the quench, or some remembrance of the initial conditions there in your solutions too?
I think the memory of the quench is there in the critical value of epsilon. Actually, if you look at the temperature formula for the black hole, then you see it is square root of some critical value, okay, which is the value of which characterizes the state at that time, capital T, of the system, and minus some epsilon 1. So,
but actually my
yes,
question
there is a memory. Yes.
Yeah. But my question is not simply about how much energy you are putting into the quench, like for example, but so energy is one parameter. Say that I want to remember both the width and say the duration, the amplitude. So what was happening in our case, you are remembering something more than the total energy. It is something beyond that. Yeah.
I see.
So it would be interesting to see if it happens in your case too, actually.
Yeah. So here, of course, energy is not really conserved for all time. I mean, so we had to, it's conserved for a certain time from 0 to capital T, and then of course, because there's a quench which is really time dependent.
Yeah, but that doesn't. I think it's not the main difference, because in our case, the quench and the system black hole is evolving simultaneously. So total energy is conserved. It might be interesting to see if you do not make this interaction, whether there is still some memory of the quench beyond the energy that you're dumping.
Okay. I'm not familiar with your formulation, so maybe I'll look at it and then we can discuss.
Okay, thank you, Spenta.
Yeah.
Gautam has a comment to Ayan's question. Maybe Gautam, you'd like to comment here?
Yeah, so my comment was that, the perturbations that we apply, they do not preserve the SL2R. So it's not, except in the adiabatic limit, in which you can tag the SL2R charge and what's going on. But we are doing a sudden quench, and therefore, I don't think we can, we can talk about SL2R.
Okay, then it is different. Okay, in my case, I even my perturbations do preserve overall SL2R. Also, non-local. It's a non-local in time. The charge becomes non-local in time, but still it preserves SL2R. Yeah. So maybe this is why it is different. Then. Okay.
I think so.
Other questions? Okay, so if there is no further question, let us thank Spenta again, and also all three speakers of the morning session. And we meet again in the afternoon.
Thank you, Debashish, for conducting this, and thanks everyone. And please, speakers, go to Slack and answer questions. Thank you. See you soon.
See you. Bye.